So now we're going to talk about Eigrp, the Enhanced Interior Gateway Routing Protocol. We talked about this protocol a little bit prior when we were doing our introduction to dynamic routing. It is a distance vector protocol, but it does take a lot of characteristics from link state. And let's go ahead and talk a little bit about some of those fundamental concepts in the chapter here. Right? It was released in 1992 as a Cisco proprietary protocol, but in 2013, the basic functionality of the Eigrp was released as an open standard, and it now falls under the IETF umbrella, just like OSPF does. Eigrp, when we say the basic functionality, being able to set up a basic Eigrp network, but some of the enhanced features like stub routing and whatnot are not included in that open standard release. It is an advanced distance vector protocol, right? So we talked about the concept of advanced distance vector when we were doing our original discussion, right? And how advanced distance vector is a little bit limited because it doesn't have a complete picture of the entire network. It does routing by rumor. And unfortunately, Eigrp still falls within that group that RIP falls under and Eigrp falls under, but it doesn't do periodic updates like most advanced distance vector protocols do. And it does bounded updates, and it only sends out routing information when necessary and so on. But fundamentally, it is still a distance vector protocol. So Eigrp is a little bit deficient in what it knows about the network topology. So there are some things that are going to have to be implemented, like feasibility condition checks, looking at reported distances, looking at feasible distances, and we'll get into all that in the next few slides here. All right? It uses an algorithm called the Diffusing Update algorithm to make its decisions on how to route to destinations. We are going to learn all about that algorithm in this chapter. We're going to learn about how the calculations are done. We're really going to get into the weeds with this protocol, all right? As well as OSPF when we get into the OSPF chapter. Unlike RIP, Eigrp routers have to establish official neighbor adjacencies before they exchange routing information. A neighbor adjacency means that it's almost like a TCP connection establishment. Two routers that want to exchange routing information say hello to each other, they negotiate, well, they don't negotiate, well, I guess they do negotiate some parameters, but they verify compatibility, K-values, authentication, common subnet, and so on, to see if they can actually become neighbors. Eigrp routers do not exchange routing information unless they're neighbors. All right? So even if I see another Eigrp router, if I can't form an adjacency with that neighbor, I'm not going to exchange information with that router. So obviously, logically then, the very first thing you want to verify in this protocol is your adjacencies. That's the first step in Eigrp. It's kind of like saying, if you're going to troubleshoot connectivity in your network, do a show IP interface brief and check layer 1 and layer 2 first before you start troubleshooting layer 3. Well, in Eigrp, the very first thing you want to do is look for those adjacencies. And we're going to talk about how we do that in this chapter. All right, Eigrp runs directly on top of IP. So there's no transport layer function. Now, we know IP is connectionless. It's best effort. So we don't have any guaranteed delivery of datagrams in IP. So Eigrp employs the use of another protocol called the Reliable Transport Protocol that provides those connection-oriented functions. All right. Now, we don't see RTP listed in the frame payload. This is my layer 2 header. This is my frame check sequence. Here's my IP header. In the protocol field of that IP header, I'm looking at protocol 88. And then my packet payload is this a hello packet? Is this an update? Is it a query? Is it a reply? Is it an acknowledgement? There's 5 packet types in Eigrp. So the packet payload is the actual Eigrp information, which includes the packet type header plus the type, length, and value fields that you would see carried in Eigrp. All right? Eigrp does partial bounded updates, meaning that it only sends routing information when necessary, which is when something changes, and it only sends up those changes. It only sends out those changes. It doesn't send out everything. It only sends out the things that changed. All right? Now this is interesting, and we're going to see this towards the end of the chapter. Eigrp actually supports equal and unequal cost load balancing. This is on the test as well. All right? Equal cost load balancing means what? Any ideas? You were right the first time to say metrics, right? If the metrics are the same for a destination over multiple links, I will use those links equally to route traffic over both links. But Eigrp is the only routing protocol that supports unequal cost load balancing, meaning that I can even load balance over links that don't have the same metric. It doesn't do it by default, but we'll see how that works, okay? So just to summarize again real quick, Eigrp is a distance vector protocol. It does incremental and bounded updates. It runs on top of IP using protocol 88. It establishes neighbor adjacencies before sending and receiving routing information. And it uses RTP as kind of a TCP type function, meaning that gives us sequencing, it gives us acknowledgments, and so on. Okay? Now, as a protocol, there are 3 data structures that have to be created in order for Eigrp to function. We talked about these data structures when we started talking about dynamic routing yesterday. The data structures include things like neighbor table. Guess what goes into my neighbor table? A list of what? My neighbors, right. And then I have a topology table. We talked about this yesterday. What goes into the topology table? Everything that I'm learning from every neighbor, including all the stuff that I may not use, right? So in the case of Eigrp, what goes into the topology table are successor routes, which we'll learn about, feasible successor routes, which we'll learn about, and the third type of route, which is a route that doesn't qualify as a successor or feasible successor, which would be the routes that potentially could be loops in the network. All right? So the first thing we do is we establish our neighbor adjacencies. That goes into the neighbor table. The second thing is we collect all the information from those neighbors, which is routing information. Okay? And then the third thing we have is our routing table. Now, the routing table is not specific. The routing table is not specific to Eigrp, right? It's a global routing table, and all my routing protocols, static routes, OSPF, Eigrp go in there. But the routing table is ultimately our goal, isn't it? That's where I want to get to. I want to get to my routing table, meaning that I want to be able to pick the best routes, and those go into the routing table. So these are the 3 data structures. And we create these data structures for IPv4 and IPv6. Now, looking at this slide here, if you are building an Eigrp network, what do you think the first thing you want to verify is? If you're having problems with convergence, if something's not showing up in a routing table, do you start analyzing routes? No. You look for neighbors. Because if I don't have neighbors, I'm not going to learn routes, right? So you look for the neighbors in your neighbor table. We're going to do a lot of this in real time when we go through our lab exercise as well. All right? So remember we talked about data structures. We talked about the next thing was routing protocol messages. Routing protocol messages. These are the messages that are used by the protocol to disseminate information. All right? There are 5 different routing protocol messages that exist. And by the way, this is not a typo. Hello messages and acknowledgments have the same message type. Message type is actually a number that applies to the message itself. So there's a message type of 1, which is an update. There's a message type of 3, which is a query. There's a message type of 4, which is a reply. Message type of 5, which is a hello. And a message type of 5, which is an acknowledgement. All right? Now, throughout this course, we've been looking at headers, right? We looked at a data link layer header in detail. We looked at packet headers in detail. We looked at transport layer headers in detail. Well, this is an Eigrp header. I'm not going to pull one up in Wireshark because we don't have Eigrp in our environment here live, but let's go ahead and take a look at what the header looks like. Version. Naturally, there's a version field because we have Eigrp for IPv4 and we have Eigrp for IPv6, okay? The opcode field represents this type field here. So opcode will tell whoever's processing this datagram what type of message it is. If the opcode is as 1, then we know this is an update. If the opcode is a 4, we know this is a reply, and so on. The checksum. You guys know what a checksum is. All right? Checksum allows us to verify the integrity of information that's being sent and received. It's like a frame check sequence. It's a hash value that goes into that field to verify the integrity of the information. And we've seen this many, many times in a lot of different headers. TCP, UDP, IP. IPv6 doesn't have one. Even Ethernet has one in the frame check sequence. Flag fields, we know that flag fields are used for all kinds of things, right? Flag fields are used to indicate special transactions that take place between routers. There are 32 bits reserved for flag fields here. We're not really going to get into the flags in this class, but those flags can be adjusted based on what type of message it is and what are the parameters of the message and so on. Quite frankly, in a basic understanding of Eigrp, an understanding of those flag fields is not really that important. Sequencing and acknowledgement. This is the reliability component to Eigrp. Remember, Eigrp doesn't use a transport layer protocol. It's not carried inside of layer 4. So in order to provide reliability, in order to provide those reliable functions, we have sequencing and acknowledgements. And it works pretty much the same way that it does in TCP, right? Sequence numbers, acknowledgement numbers are directly related to sequence numbers to identify that I've received packets and so on. Perhaps one of the most important aspects of the Eigrp header is this right here, the Autonomous System Number. It's called an ASN, Autonomous System Number. And this is unique to 2 protocols. BGP uses an Autonomous System Number, and Eigrp uses an Autonomous System Number. We talked yesterday about what the concept of an autonomous system is. It's all the routers that are speaking the same language, basically. All the routers that are speaking the same language and that are partnering together to communicate information, right? You can kind of think of it as a cloud that represents your enterprise of Eigrp routers, right? In Eigrp, we use a number to define that membership. We use a number to define that membership. That number has to match on all of the routers. That number has to match on all the routers. Very, very important, and that'll be on the test as well. The ASN has to match. Now, it's a number you can pick. It's kind of an arbitrary number. It doesn't matter what the number is, but you have to choose that number. We didn't see that in RIP. RIP doesn't use an autonomous system number. You choose it and pick whatever number is your lucky number, I guess, because there's no distinct difference between one number or the other.
But you just said it represents all the systems in the same.
Represents all the routers within the same autonomous system. Now, as far as configuring the number specifically, we'll see that when we go through our Eigrp configuration.
I pick it.
You pick it. No, the router does not pick the autonomous system number. You, as an administrator, select the number. That's why I said pick your lucky number. Right.
That's how I decide who is in my system.
That's right. That's right.
The ones I control. I can't control someone else's
right.
router.
but this number does have to match. Now, interestingly enough, it is a 32-bit field, but the number is from 1 to 65,535, which is like a 16-bit number, right? I imagine that, well, I don't really imagine, actually, that it would ever grow from that, because these autonomous system numbers are internal. They're not published on the internet. These are private numbers, and you get to pick whatever number you want, okay? But it is a 32-bit field. Now, very important, this is the packet header for Eigrp. So if you can imagine, frame header, IP header, Eigrp header, okay? The gray box that you see here is the Eigrp payload. So there's more information that's carried inside of Eigrp. It's not just the header itself, and we're going to see this information as we go through the chapter, but the payload is relevant to what type of message it is. If it's a hello, for example, there are hello-specific components that are carried inside of Eigrp. Yes?
So from a security standpoint, in some ways, is the ASN, is that something that somebody could open up the packet like Wireshark and read?
Absolutely. The question was, if somebody captures an Eigrp message, will they see the autonomous system number in Wireshark? And the answer is yes, which is why passive interface is a good idea. It's also why running authentication is a good idea. We don't really discuss authentication in this course. We should, but we just don't have enough time. We certainly talk about it in CCNP. But you should never really implement a routing protocol without implementing its authentication features. Anything that's dynamic in nature, if you can secure it in that form, you should, right? Yeah, this is not encrypted information. It is multicast. So if you have multicast scoping and you have multicast configured in your network appropriately, people shouldn't see this information. But quite frankly, most people don't configure their environment securely with multicast. So multicast messages are treated just like broadcast messages from a switch perspective. So yeah, it's entirely possible that somebody can see this information. I mean, if I'm not running authentication in my domain, what is the only thing I need to know to insert a rogue router in the network? What is the only thing I need to know? Well, IP addressing, of course, but I'm already a member of that subnet, so I know what that is. I need to know the autonomous system number. If I know your autonomous system number, I can throw a router on the network and become part of the domain and start injecting routes. Okay? So very, very important to run authentication as well.
Is that type field the same type field?
No. It has relevance to each payload. It's payload specific, right? It's payload specific, yeah. All right. So there are always two parts to routing protocols, and I mentioned this on day one, and I'm going to mention it again for the folks that will be watching this on YouTube. There are two aspects to understanding routing protocols, or anything in networking for that matter. There is the ability to implement something, and then there's the ability to understand the principles of something, what I call the engineering principles, right? I can teach you guys how to implement Eigrp in about 15 minutes. But that doesn't mean you understand fundamentally how the protocol operates, or its function, or how it makes calculations, or the math involved, right? It's kind of like you can use a subnetting calculator to calculate subnets, but that's not really an engineer, right? An engineer truly understands the protocols and can look at a topology and manipulate a topology in any way that they want and have a complete understanding of what the effect of those manipulations are, okay? It's a protracted discussion, but for me, it's really important to teach you guys this because I want to make you network engineers. I don't want to make you network technicians. I don't want to make you network administrators. A network administrator is somebody who takes a configuration and pastes it into a router. and then knows some basic show commands to verify. A network engineer understands the algorithms, understands the back-end function, all right? Now, I got off on that little soapbox because that's what this slide is all about. It is all about the algorithm. It's all about the decisions that Eigrp makes because it is distance vector and why it makes those decisions and what the purpose of that is. So this is the theory of the protocol. There's two components we talk about when we talk about theory. We talk about the algorithm and we talk about the metrics. All right, we'll talk about the metrics in a little bit. So these are very, very important concepts when it comes to Eigrp. This is the dual algorithm. This is what the dual algorithm does. All right, so let's go ahead and get started in talking about this. The first term that you need to know within Eigrp is something called the successor. Okay, this is unique to Eigrp. In fact, all these concepts and terms that we're going to talk about are unique to Eigrp. A successor route in Eigrp is the best route, period. It's just a term that we use to describe the best route. Where, in what data structures will you find the successor route listed? I'll give you a refresher on the data structures: neighbor table, topology table, routing table. In what data structures will you find the successor routes? Sorry? Not the neighbor table. It's a route, it's not a neighbor. The topology table and the routing table. Right. The topology table contains everything. So it contains successors, feasible successors. But the routing table is the routes that I'm actually using. So a successor route in Eigrp, because it is the best route, goes not only into the topology table, but it goes into the routing table as well. Remember, the neighbor table is simply a list of all of my neighbors. Not the routes that I'm learning from them, but just that the neighbors exist. Okay? So a successor route is the path with the lowest metric. And then I have a reference here to feasible distance, which is, by the way, another term in Eigrp. Feasible distance is the metric. You'll see that listed in the topology table as an FD, Foxtrot David, right? Or Foxtrot Delta if you're trying to be more accurate. But it is essentially the metric. Okay? It's the metric. All right? And we'll see how that's calculated a little bit later on. So essentially, a successor is the route with the lowest feasible distance. You know, when you look at your routing table and you see the brackets, and the first number in the brackets is administrative distance, guess what the second number is? Feasible distance. All right? Feasible successor. A feasible successor is the path with the next best feasible distance. So oftentimes people will simply classify this as the backup path. This is one of the ways that Eigrp tries to be more efficient. Not only does Eigrp try to select the best path to a destination, Eigrp tries to pick the next best path to the destination. So if the best path fails, immediately switch over to the next best path. Okay? This is to increase convergence efficiency, decrease convergence time, and increase convergence efficiency. However, if you look at the definition here, it says the path with the next best feasible distance that meets the feasibility condition. So we're defining feasible successor by referencing another definition, which is the feasibility condition. Let's talk about feasibility condition. Very, very important concept in Eigrp. Here's the definition of feasibility condition. I'm going to mention this a couple of times. It usually takes students about 3 or 4 times going through it to actually figure it out. Feasibility condition. A backup path is only considered a feasible successor if the reported distance of that path is less than the feasible distance of my current successor path. What? Exactly. Feasible successor if the reported distance of the backup path is less than the feasible distance of the successor path. So we have to break this down, and I drew a little diagram here to kind of help you guys understand what we're talking about. All right? Very important concept. Feasibility condition, feasible successor, has nothing to do with the best path. Ultimately, the best path is chosen based on only one value, and that is the path metric. All right, which is the distance to get from point A to point Z. So in this case, the feasible distance of this path is 2,000. The feasible distance of this path is 2,500. Which path becomes the successor? Right, the top one. The one that has the lowest feasible distance. So just to be clear, that is really the only consideration when we're trying to pick our best path. All this other stuff we're talking about, feasible successor, reported distance, feasibility condition, has nothing to do with selecting the best path. Okay, you guys got that? All right. But so router 1 has said, okay, this is my best path. So I'm going to use that path to reach network X. But what router 1 also wants to do is it wants to make an evaluation. It wants to say, okay, I've picked my best path. Now let me go and see if I can find a second best path. So if my best path fails, I can immediately start routing over the second best path. This is just to simply decrease the amount of convergence time it takes so that I can continue routing with the little impact or no impact on the network topology. Let me read the evaluation, and while I'm reading the evaluation, I'm going to be circling things on the diagram to kind of visually get you guys to see this. Feasibility condition, a backup path, which would be this path, agreed? A backup path is considered a feasible successor if the reported distance, here's reported distance. By definition, the reported distance is the cost for my neighbor to get to the same destination. It makes sense that it's called reported distance, doesn't it? Because this is the distance that R3 is reporting to R1. Make sense? That's why it's called reported distance. Some people call it advertised distance, but then that makes it confusing. You get that confused with administrative distance. So I tend to call it reported distance. You'll see it documented both ways. But advertised distance and reported distance are synonymous terms. Sorry? Rumored distance, yeah, you could actually say that. I've never heard it called that, but it makes sense. It is routing by rumor. Suksan, you had a question? You have to, the air conditioner is really loud, sorry. Then there's no check for feasible successor. Yeah, if you only have one path, that's it. That path is automatically successor. There's no check for a backup path. And by the way, if there are multiple paths, 3 or 4 or 5 or 6 paths, we're going to do a feasibility condition check on all of them. We may only have one feasible successor, but we're still going to check all the paths to see if they meet the condition. All right? Yes, exactly. And this is what the algorithm does. This is the whole point of the algorithm. It's not just look at a metric and pick the best path. There's a lot of other things that are going on so that the protocol is more efficient, right? Right. Exactly, exactly. And you might look at this and go, well, why is Eigrp doing this? I mean, clearly the top path is there and the bottom path can be used, but we'll get into that in a second. It's because it's distance vector, right? But we'll get into the details of that. So let's continue on. The feasible successor path, backup path, if the reported distance is less than the feasible distance of the successor. Okay? 1,500 is less than 2,000. Agreed? So this path is a feasible successor. As long as the reported distance of the backup path is less than the feasible distance of my primary path. Remember, feasible distance is the whole metric. Reported distance is the metric for my neighbor. If the reported distance is less than the feasible distance of my primary path, then it is a valid backup path. Okay? I've heard this before. Somebody being a feasible successor, right? And I'll explain what happens when I have a feasible successor and when I don't, because Eigrp behaves differently in those scenarios. But I've heard people say, well, wait a minute, if the reported distance is 1,500 and that's lower than 2,000, why wouldn't that be my best path? It's my neighbor's cost. The link to my neighbor increases the metric more, which might make it more than the overall path cost for the other path. So you can't forget that link between you and the neighbor. All right? So why do this check? Why do this check? Well, as I mentioned before, Eigrp is distance vector, which means it doesn't have a complete picture of the topology. We see the whole topology here. And by looking at this topology, we can see what goes where and so on. But Eigrp doesn't. In fact, Eigrp pretty much sees up to that point, and that's it. It does routing by rumor. So because it doesn't have a complete picture of the topology, it has to do these sanity checks to make sure that the backup path is not part of the original path. I'm going to draw a diagram that will describe that concept in a little bit. But let's wrap up this part of the discussion first. So now we've confirmed that we do in fact have a feasible successor. Here's my successor path. There's my feasible successor path. Okay? Question. What happens if router 2 goes down? What do you think should happen? It switches over to the feasible successor path without doing really any kind of major calculations. There's some minor calculations that are done, but essentially convergence is almost instantaneous because we've already verified the validity of that backup path. So the feasible successor essentially gets promoted to successor. And then we might select another feasible successor if we had a third path or a fourth path or a fifth path. Where does the feasible successor route get stored? Feasible successor route gets stored in the topology table. Right. Remember, the topology table is everything that I know. The routing table is everything that I'm using. Feasible successor paths are not being used. They're backup paths. The only thing that goes in the routing table is the best path, successor. So you will find your feasible successors in your topology table. All right. What if it didn't meet the condition? What if this number here wasn't 1,500, but it was 2,000? Okay. Is this number less than this number? And the answer is no. Equal doesn't count. It has to be less, which means that this path here does not meet the feasibility condition, so it is not a feasible successor.
But it is still in the topology table.
It's still in the topology table.
So in the event of failure of R2,
it would then blank because we don't know what it then does, right? You might have an idea of what it then does, but it is still a route.
Right.
It's not that R1 said, I can never use that path. The convergence time is longer, and here's what happens, which brings us into, by the way, this message type, query. Okay? Because if R2 fails here, or anything along that path fails, because R1 doesn't have a feasible successor, it knows that the path through R3 exists, but it didn't meet the condition. R1 sends a query to R3. That is one of our message types. R1 sends a query to R3 and says, hey, I lost my best path. You're reporting a path. I didn't know if that path was part of my original path or not. So tell me, do you still have a path to network X? R3 then sends a reply. By the way, that query propagates down the line, but R3 then sends a reply and says, yeah, I still have a path. Then at that point, I insert that route as my new successor. So I can still use the path, I just have to do an additional step to verify that the path is still valid. All right?
To complicate that scenario, there was more between R2 and the next hop and the next hop. If some of those links go down, and R2's path, which also has a redundant path,
right,
if that gets longer and longer, at what point do I then reevaluate? Well, that's being reported. So then at some point the background process realizes that the current path is not the best path.
right.
And the logic takes over and says, oh, even, whether it was a successor path or not, it will evaluate the better path and then switch things.
Right. And these evaluations are constantly going on, right? Remember, in EIGRP, whenever anything changes about any path, we always reevaluate these numbers, right? So what might have been a successor at one point, even though the path, the neighbor is still the same, the next hop is still the same, if the metric changes, all of a sudden that path might not be the successor because it might have a worse metric than another path in my topology. So anytime there's a topology change, we're constantly evaluating this. Even if a new path comes online that didn't exist before, even if it doesn't beat out the successor, it still gets evaluated. It still goes in the topology table. We still try to identify whether or not that path meets conditions and so on. Okay? I'm going to explain one more thing about this slide, then we're going to move on. All right? This is a diagram that I typically use to describe the reason why it is important to do this feasibility condition check. All right? Because when we talk about a loop in the network, we're not talking about the loop that we had in that original diagram. We're talking about a loop like this. Right? So we've got network X in the cloud. And obviously there is a metric to get to network X here, which is a feasible distance to get to network X metric, right? And by the way, this is all from the perspective of R1. Now R1 is then going to advertise that network to R2, and R2 is going to advertise that network to R3. Potentially, R3 might then advertise the same network back to R1. It's actually technically not supposed to happen because we're supposed to have another feature called split horizon. Split horizon says don't ever advertise a network out the same interface you learn about it on. And you would suspect that if R1 is advertising to R2, it would also be advertising to R3. But let's say for some reason that wasn't the case. This advertisement didn't go over there, so split horizon doesn't apply. So now R1 thinks it can get to network X two different ways. It thinks it can get to network X this way, and there's a feasible distance there, and it thinks it can get to network X the top way. Now clearly the path that's chosen is the top path, the blue path, because that has a lower feasible distance. Okay? But the bottom path is actually kind of a ghost path, isn't it? It's not a real path because it includes the original path. See what I'm saying? Now, as far as router 1 is concerned, it doesn't know that because it's distance vector. So we have this feasibility condition check. Let me use orange in this case. This is the reported distance of that path. to R1. That's the reported distance of the path to R1. Is there any way, mathematically, that that reported distance could ever be less than the feasible distance of my primary path? No. Because the reported distance includes my primary path. Doesn't this report, if you kind of do a little dotted line here, doesn't that reported distance include my original path? That's what the feasibility condition check is looking for. It's trying to determine whether or not it doesn't mean it is, but it means there's a possibility that the original path could be included. And all this stems from the problem that Eigrp is a distance vector protocol. Link state protocols don't have to worry about this because they have a complete picture of the topology. Did that help clarify that concept a little bit? Yeah. This is the algorithm. This is the Eigrp algorithm. Yes?
Would it eliminate that route if it didn't qualify for that?
Well, let's go through the scenario. I erased it already, but let's go through the scenario. If the primary path fails, which means some router upstream failed, router 1 is going to send a query down to router 3 saying, do you still have a path? Of course, router 3 is not going to have a path anymore. So router 3 is going to say, no, I don't have a path anymore, which then confirms my suspicion that it was a loop. You don't meet the condition. Always, right. If I learn about a route, I still consider that a possibility, no matter what. But if it doesn't meet the feasibility condition, I go through additional checks if I have to use that route. Right, always. Feasible successor is always chosen, right? Let me do another diagram real quick. So here's a route, here's a route, here's a route. Excuse me. And here's a LAN. Here's a route. And then here's a route, here's a route, and then that goes into the LAN. So I have 3 potential paths to get to the destination. In fact, let me make this even better. 3 distinct paths to get to that destination. No one path, requires any of the other paths. Eigrp doesn't know that. As far as Eigrp is concerned, the visibility is up to this point. It really doesn't know what follows those routers. So if I have a feasible distance on this path of 10, and I have a feasible distance on this path of 30, and I have a feasible distance on this path of 40, clearly I'm going to use the top path as my primary path. And that's the only thing I evaluate when I'm looking for the best path. But then if I have reported distances, reported distance of this path is 8, and the reported distance of this path is 20. Now I'm doing a secondary evaluation. I'm saying, okay, which path is my successor? This one. Which path is my feasible successor? This one. Which path doesn't meet the condition? This one. See what I'm saying? Because the feasible distance of this path, the reported distance of this path is greater than the feasible distance of my best path. But what happens, see if I can clean this up a little bit, what happens if I lose my successor path, right? What happens if I lose my successor path? This router goes down, gone, right? Which path becomes my successor? This path becomes my successor. Do I have a feasible successor now? And the answer is yes, because I've done the evaluation all over again, and I said this path now meets the feasibility condition, so it became a feasible successor. because the feasible distance here is less than the God, I keep saying that wrong. The reported distance here is less than the feasible distance here. Right? Right? In that case, that scenario I just described, I would never send a query. I'm not going to query the bottom path because I already had a feasible successor. All right? All right. You guys following along? Now, variance we're going to talk about at the end of the chapter. This is the feature that allows us to do unequal cost load balancing, variance. Okay, but we'll get into that at the end of the chapter. So that is really the hardest aspect of Eigrp, understanding this logic. Now, there's some other aspects to Eigrp we don't talk about in this level. We talk about it with CCNA, authentication, query scoping, being able to filter out queries, and what we call stub routing feature. Eigrp supports stub routing, and don't really want to get into that right now, but it's just another enhancement to make Eigrp more efficient. All right? All right. So let's talk about the 5 packet types in detail. Hello packets. Eigrp hello packets are used to form adjacencies. All right? They are sent unreliably. Now, what that means is they're not acknowledged. Hello packets are not acknowledged because that would be a little bit redundant. You send me a hello, I send you a hello. You send me a hello, I send you a hello. I'm not going to send you a hello and then you're going to acknowledge and send me a hello, and I'm going to acknowledge and send you a hello and acknowledge. There's no point in doing that. So hello packets are not acknowledged, but they are sent in multicast. The multicast addresses that are used in IPv4, it's 224.0.0.10. In IPv6, FF02:A. Makes sense. A is 10 in hex. FF is multicast, and 02 represents the scope, and so on. All right? These hellos are periodic, which means they're sent out every X number of seconds. On 1.544 meg links or below, we send them out every 60 seconds. Okay? And anything faster than 1.5 megs, we send out hellos every 5 seconds. Now, that might seem like a lot of hellos. But remember, the goal of any routing protocol is to converge quickly. So I want to make sure I'm maintaining these hello packets are extremely important. They allow us to establish the adjacencies. All right? Here's what a hello packet looks like. In this case, we're looking at HDLC. These are serial links, so that matches up with the fact that we're using HDLC as our protocol, our encapsulation protocol. Here's the Eigrp packet header. All right? Let me do that again. Here's the Eigrp packet header. Remember, that was the white box that we saw, and then the gray box is the payload. So this is the hello, and this is the header. So it's version 2, so that's Eigrp for IPv4. The opcode is 5, and as you can see, that's hello and acknowledgement. Remember, that was the type code that we saw in the column. Here's our checksum. No flags being used in this particular case. The sequence number is 0, the acknowledgement number is 0 because hellos are not acknowledged or sequenced. They're sent unreliably. Our ASN is 12. So this is a Wireshark Capture. You can actually see the autonomous system number simply listed in the Wireshark Capture. And then these are our hello parameters. What is actually carried inside of hello? Software version. Okay, which is actually important because some versions of Eigrp are not compatible with other versions of Eigrp. Something called a hold down timer. Now in this case it's 28 seconds. We'll talk about why it's 28 seconds in this case. We'll talk about what a hold down timer is in a second. And then these are the parameters. Remember I said that the type field is specific to the payload? It's not the same thing as, it's not the same thing as an opcode. All right, even though in the header it showed, you know, opcode here and type here. I should probably rename this column. It says type. It really should say opcode because it doesn't have anything to do with type here. In fact, before I forget to do it, I'll just go ahead and change it now. That way, the next time, it'll be correct. All right. Oops. Hold on. Ah. Oh, come on. Come on. Yes. All right. So that makes more sense. Opcode specifically refers to that field in the header. So the gray box that you see there, that is our payload. In this case, the payload is the hello parameters. Yes. They're equally important in link state. Right, but it's two phases, right? That the hello packets are used to find and become neighbors with other routers, right? So it's the chicken or the egg. Well, in this case, it's not. It's the horse before the cart, right? Because you can't get routes, you can't verify topology until you have neighbors. So the hello packet is equally as important in OSPF because I can't get routes and I can't learn about the topology until I have neighbors. What do you mean acknowledgement packets? Yes. Yes, so hellos, because they get sent out on a periodic basis, you're right in a sense that it's a little bit redundant. But again, I need to know when my neighbors go away, right? Because a neighbor might go away for physical layer problems. And in that case, if it's a point-to-point serial link, for example, if this serial link goes down, if this serial link goes down, we lose our physical layer and data link layer status. So I know the neighbor's gone at that point. But in Ethernet, that's not the case. If I have an Ethernet network, if somebody unplugs the cable from that router, my network is still active. So there's no way for me to tell whether or not that neighbor's there or not. I can't rely on physical layer or data link layer functions to identify whether that neighbor's still there. So what I need to do is I need to say, okay, I'm no longer receiving hellos from that neighbor. If I stop receiving hellos from the neighbor, that's an indication that the neighbor doesn't exist anymore, which is an indication that the routes that I learned from that neighbor aren't valid anymore. Not necessarily, and here's the reason why. Just because OSPF has a complete picture of the topology doesn't mean it went out on its own to discover that. It still learned that picture from its neighbors, right? I still obtained the topology information from my neighbors. Even though I have a complete picture of the network, that picture was built based on what my neighbors still told me. And if the neighbor's gone, I need to know, because then that means that that path or those paths that that neighbor advertised are no longer available to me. It's not like a link state protocol is constantly going out and evaluating the paths. It's just building a picture, and it's a static picture. It's not a living picture. I don't know if that makes sense. Yeah. So, right. It's within your autonomous system. Right. Right. So we get to this concept of dead timer. Okay? The hello timer is the hold time, the hold time, which is also often referred to as a dead timer, identifies how long I'm going to wait if I don't get a hello from a neighbor before I decide to delete that neighbor from my database. So if it's 3 times and I'm on an Ethernet network, I'm getting hellos every 5 seconds. Now, if I miss a hello in 5 seconds, okay, no big deal. If I don't get a hello in 10 seconds, no big deal. But as soon as I don't get a hello in 15 seconds, then I make the assumption that that neighbor no longer exists. I delete that neighbor from my database, and anything that I'm learning from that neighbor also gets removed from the topology table. Right? Because if the neighbor's not there, then whatever the neighbor told me about shouldn't be in my database. Successors, feasible successors, everything else, which it could affect everything, right? Right. Right. Yes. No. It doesn't get suspicious, right? It just basically thinks, yeah, it's black or white. It's like the neighbor's there, the neighbor's not there. Period. It doesn't start to try and do intermediary things as hellos disappear. So yeah, it's just black or white. Okay. Which, by the way, can be a bad thing, because if I'm relying on routes based on neighbor relationships, potentially it could be 15 seconds before I converge if something changes, right? So that can be kind of a bad thing. That's why you kind of have to tune some of these things as well, which we don't get into in this class. All right, so what's in the hello? We've got the size of the hello information, which is the payload of the type length value fields. We've got these things called K values. K values are very important. These values have to match on all of the routers in order for them to become neighbors. We don't know what they are yet, but we'll get into that in a little bit. We've got the hold timer. Now, in the case of OSPF, the hello timers and the hold timers have to match to form an adjacency. In the case of Eigrp, these timers are negotiated. The timers are negotiated. So they don't have to match. All right? So out of all of this configuration here, ASN has to match, K values have to match, and a lot of times Eigrp versions have to match as well. Okay? This is the first step in the convergence process. Send and receive hellos, establish neighbor adjacencies. Once I've established my neighbor adjacencies, the next step in the process is sending routing information. I've built all my neighbor relationships. Now I want to send my routing information. Okay? So this is done in the form of a routing update. Now, updates are used for initial convergence, but they're obviously also used for changes in the topology as changes occur as well. Agreed? So an update is not just sending, the initial information. It's also sending the additional information when something else changes. All right. So updates allow us to send out routing information during our initial convergence process. Updates also allow us to send out changes in routing information. Okay? So you see here, these are partially, we send out partial updates, which means we don't send out our entire routing table. We only send out what changes. These are bounded updates, meaning that they only need to go to the neighbors that need to see the information, and updates are acknowledged. So they're going to have a sequence number, they're going to have acknowledgement number, and so on. In fact, we see that here in the Wireshark Capture. Here is the header, again, and here is the actual, update payload, if you will. In this particular case, the update that's being sent is based on a network that went down. It's called a triggered update. So the 10.0.0.0/8 network went down, and the router's sending out an update to its neighbors saying that this route is no longer reachable. It's an internal route. External routes in EIGRP are routes that are redistributed into EIGRP. Those are those DEX routes that you saw reference to in the administrative distance table. Okay? And we see the metrics for the route, the delay, the bandwidth, the reliability, the load. These are all metrics that EIGRP uses. All right? And some other update information is being sent here as well. Queries and replies. We talked about queries. We talked about replies. A query is sent whenever we lose our best route and we don't have a feasible successor. Queries are all sent reliably, so they're sequenced and acknowledged. They're also, sent out whenever there's a change in the topology, but only when we lose our successor and we don't have a feasible successor. And queries are acknowledged. All right, so a query is essentially a request for information. A route goes down. I no longer have a path for that destination, but I do have some other paths that could potentially be used. I just have to go through the process of vetting those paths before they're actually used. Okay.
Do hello and share Opcode 5 because acts as a hello.
The payload is different.
Right, but I mean,
but they're kind of
require a hello if it's getting an act to other operations.
No, that is not true.
Okay.
Hellos always get sent. All right? Hellos always get sent. So here's the general process for adjacencies. In OSPF, it's a little bit more complicated. We have the down state, the init state, the two-way state, the xstart state, the loading state, the full state. But in EIGRP, neighbors exist or they don't exist. So I turn on EIGRP on the interface. It starts generating hello packets, and then of course the other side is also sending hello packets. And eventually, obviously we're going to add each other to our neighbor table. Then we exchange routing information through the use of updates. We acknowledge those routing information. That routing information, by the way, goes into the topology table. And then I run my algorithm against that information, and I build my routing table. So those are the three data structures that we talked about, kind of the progression that we go through to converge, to build our convergence. Neighbor table first, then topology table, then routing table. Make sense? I mean, it seems logical, doesn't it? Kind of makes sense. All right? All right. The last theoretical piece that we're going to talk about before we actually start to get into configuration is metric. There is that metric that I referenced yesterday. The metric is K1 times the bandwidth. And bandwidth, by the way, is 10 to the power of 7 divided by the minimum path bandwidth in kilobits per second times 256 plus K2 times the bandwidth divided by 256 minus the load plus K3 times delay. And delay is cumulative delay in the interface delays in microseconds divided by 10 times 256 times K5 divided by the reliability plus K4. And hop count is looking a little bit better now, isn't it? All right. But this is what we call a composite metrics. a composite metric. And it's a complex metric, but it's not as complicated as it seems. First of all, the K values. These K values are multipliers that you can adjust in the router to change the effect of specific components of the metric. Obviously, if I increase K1, bandwidth becomes more important in the metric. If I increase K2, bandwidth and load become more important. If I increase K3, delay becomes more important. You get the idea, okay? But if you look at the default K values, K2 is 0, which means that part of the formula goes away. K4 and K5 are 0, which means that part of the formula goes away. All right, I know there's a multiplication here, but the rule is if K4 and K5 are 0, we ignore that. Which means that the bandwidth and the delay are the only things that are used to calculate the metric. So in the end, and by the way, K1 and K3 are 1, so you can kind of ignore those. So in the end, the metric is bandwidth plus delay. Test question, right? Bandwidth and delay are used as a component of a metric for Eigrp. Metric calculations are extremely important, obviously, because that's how we choose our best paths. All right? Metric calculations are very important because that's how we choose our best path. So it's important to understand how these metrics are calculated and how we reference them. So let's break this down. And in the end, it's going to be pretty simple. Bandwidth. Let's break down bandwidth first. All right? So bandwidth is 10 to the power of 7 divided by the minimum path bandwidth in kilobits per second times 256. So what I mean by the minimum path bandwidth, if I've got a serial link, an Ethernet link, and a serial link, and whatever, along this path, one of those links has the worst bandwidth. Whichever that value is, that's what goes into the formula. Okay? Now, when we talk about bandwidth, remember we said this before, we're not talking about throughput. I'm not talking about congested links versus non-congested links. We're talking about a static value that is theoretical based on the interface. If you do a show interface, you can see the bandwidth value for the interface. That is the value that's used in the formula. Ethernet interfaces have a specific theoretical bandwidth. Serial interfaces have a specific theoretical bandwidth, and so on. So bandwidth is a theoretical value, not a practical value. That's 128,000 K. All right? So the other thing that we notice is it's along the whole path. So it's not cumulative. It's not something we add up along the path. We just simply pick the worst one along the path, and then that becomes the bandwidth that I use. The other part of the metric is delay. Okay? Delay is cumulative. Delay is cumulative. So again, I've got all these different links between routers. And by the way, guys, when we do our lab, we're going to be playing with these values, and I'm going to show you practically how to look at these values as well. We're not just simply going to look at the formula one time and say that's now how. We're going to look at it in our topology as well. So delay is the sum of the delays along the path. So this delay plus this delay plus this delay. And delay is also seen with show interface. Delay is also seen with show interface. Now, if you look at the delay value on the interface, it's in microseconds. But in the formula, it's tens of microseconds. So that's why we have to divide by 10. One other very important aspect one other very important aspect is only egress values are considered. In any metric, whether it's OSPF, whether it's EIGRP or ISIS, egress values are the only values that are considered. So if I'm trying to figure out the metric for R1 to get to network X, I'm going to look at the bandwidth and delay on that interface, the bandwidth and delay on that interface, the bandwidth and delay on that interface, and based on those values, I'm going to decide what goes into the formula. Ingress values do not matter for metric. So if I want to manipulate the metric in that direction, I have to change bandwidth or delays on those interfaces specifically. All right? Also, there's no floating point math. So if I have an interface that has a bandwidth of 1,544 kilobits per second, I take 10 to the power of 7 divided by 1,544 kilobits per second. That equals 6476 point blah, 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 blah. You drop the point blah, 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 blah. There's no fractions. You don't well, you round down, I guess. Yeah, always round down, right. So when you're putting these numbers into a formula, make sure you always drop those remainders on every individual calculation. Let me see, what does it say here? It is a bit difficult to calculate this in the exam, I guess. You're not going to have to do these calculations in the exam. They're not going to make you do that. So that is the metric for EIGRP. Again, I don't expect that you guys completely understand this at this point. But we will apply this to our topology, and I'm going to show you guys in real time how to evaluate these numbers so that you can see it actually works. All right? All right. So here's an example. I've got the router here. Oh, yeah, sorry. K values. K values are specified on a per router basis. They're configurable on a per router basis. They're not propagated through the autonomous system. But in order for the routers to all be making good decisions, common decisions, those K values have to match. You can imagine what kind of hectic environment you would have if his K values were different than your K values, because you guys would be evaluating paths completely differently. All right? Now, if you go to Cisco's website, Cisco says don't ever change the K values. At some point when they came up with the protocol, they thought that that might have been a good idea. But now they say don't even change them. Just leave the K values how they are. Don't ever change them. But if you do change them, you have to change them on all the routers. Because if I'm his neighbor, my K values are one value, they have to match him. But now that is a transitive property, right? Because now his K values have to match his neighbors, their K values have to match their neighbors, so ultimately it ends up being that the whole autonomous system has to have the same K values. All right? Now Cisco says don't change those, so don't change them. All right? So we're looking at the metric from the perspective of router 4. We're not going to do anything in the lab just yet. I just want to make sure you guys had the file, so you've got it open. Router 4, all right? Well, let me ask you guys a question real quick. How many, if you're looking at the topology diagram on the screen here, how many neighbors should router 4 have? Looking at the diagram up on the screen, how many neighbors should router 4 have? Lionel says 1, Arnold says 1, Kilesh says 1, you say 3, Pat says 3. The answer is 3. Okay? Remember, neighbor relationships in these protocols are physical. All right? Here is one neighbor. Here is another neighbor. Here is another neighbor. Switches are layer 2. They don't count. Right? From the perspective of a router, a switch is just a wire. So don't let that fool you. All right? We have 3 neighbors. All right? So router 2 is actually going to have 1 neighbor, 2 neighbors, 3 neighbors, 4 neighbors. All right? Now, that's what we were talking about. We were talking about the metric. Loopback interfaces are not neighbors. They're not routers. They're just interfaces. A loopback interface is a virtual interface, that we create on the router for management purposes, for troubleshooting. Sometimes we use it, like in this case, to generate other types of networks. But the loopback interfaces here, I mean, there's not neighbors there. A neighbor is an actual router, right? A neighbor is an actual router. So what we're looking at in the diagram below is how R4 evaluates the metric for this link here. Actually, I should draw that differently. This network here. All right. Now, if I go into the interface, the router, and say show interface gig 00, I'm capturing the bandwidth and the delay for that interface. The bandwidth and delay for that interface. The bandwidth is 1 million kilobits per second, and the delay is 10 microseconds. These are fixed values, by the way. These are values that are fixed to that type of interface. Now, if I place those numbers into the formula, bandwidth is 10 to the power 7 divided by link bandwidth in kilobits per second times 256. I get 2560. Delay is 10. The sum of the delays, in this case, we're only evaluating that directly connected network. The sum of the delays in microseconds divided by 10 times 256. So the actual feasible distance for router 4 to reach this network is 2816. Now, granted, that is a connected network. So it's not going to show up in the routing table as an EIGRP route, because it's going to show up in the routing table as a connected route. Does anybody actually know why it doesn't show up as an EIGRP route, but shows up as a connected route? It doesn't have to do with the fact, well, it kind of has to do with the fact that it's connected, right? But why? I mean, specifically why? Because connected routes have a lower administrative distance than EIGRP routes. That's why. Connected routes have an administrative distance of 0. EIGRP has an administrative distance of 90. So actually, EIGRP, because EIGRP is running on this interface, it is still part of the topology table, but it's not going to show up in the routing table. The way we look at our topology table is show IP EIGRP topology. We'll see that again later on. And sure enough, we can see that the feasible distance for that link is 2816. The feasible distance, which is the metric for router 4 to get to that network, is 2816. All right? All right. You guys following what I'm putting down, right? All right. Now we'll look at metrics. Nobody's is configured, Arnold. We haven't done that yet. All right. That's part of our lab exercise, is to actually configure this, which we're going to be doing next. All right. All right. So if bandwidth and delay are part of the metric, then how can I manipulate those values? Because there are times where you want to override the default values for the purpose of traffic engineering, for the purpose of changing how the network routes, etc. And so in order to influence that, we need to change the bandwidth or the delay. If you go into an interface and you type the bandwidth command, it changes the bandwidth of the interface. Well, not really. It changes how the router perceives the bandwidth of the interface, which is what goes into the metric calculation. Does that make sense? K values, first of all, K values, if they get adjusted, the question was, why wouldn't I just adjust K values? Those apply to every interface. Not only that, if you make your K values change, you have to change everybody else's K values, which means effectively you're not changing metrics. It's like if you multiply everything times 5, it's still the same number. It's just a factor of 5, right? So, all right. This is specific to an interface or specific to a path. All right. So the bandwidth in this case, and by the way, again, just because I make the bandwidth 1,000 kilobits a second, doesn't mean that the throughput is 1,000 kilobits a second. It doesn't. I'm not making my gig interface act like a 1 meg interface. In other words, it just changes the math. It changes how QoS analyzes the interface. It changes how metrics analyze the interface. For example, I can take a 1.544 megabit per second link and make it look like a terabit link. That doesn't mean all of a sudden I've turned my serial link into a terabit link, right? Traffic engineering, route manipulation, making traffic go over a different path. How about this? I know that the backup path should be a feasible successor because it's not a loop, but the math doesn't fit the criteria. So I modify values to make it fit the criteria so that convergence is faster, right? That's an engineering principle. People manipulate these values all the time for those purposes, right? The other thing that you can change on an interface is delay. We'll see that in the next slide. But notice I changed the bandwidth to 1,000. And sure enough, when I do a show interface, I see now the bandwidth is 1,000. And as I would suspect, the metric went up significantly, didn't it? The metric went up to 256.0256. The slower the bandwidth, the more the link costs. Make sense? All right, so I can manipulate bandwidth. The other thing that I can manipulate is delay. I can change the delay of an interface. Now, if you recall our discussion previously, delay in this case references what? Do you guys remember? Well, it's listed in microseconds, but what does it actually represent? It represents something called serialization delay, which is how long it takes for the router to process data from the transmit queue onto the wire, which, by the way, is a function of the type of interface. It takes longer for routers to transmit data onto a serial link than it does onto a Ethernet link, or fast Ethernet link, or gigabit Ethernet link. Arnold, you have a question. What is your question? All right. Let me know what your question is. If you are modifying these values, if you're messing around with these values, make sure before we do our lab that you put them back, because otherwise we're going to have a problem. All right. Now he says here he changed the bandwidth of his gig interface. He changed the bandwidth to 1,000. All right. And he goes and does a show interface on gig 00, and it's still 1,000. Or it's still, 10,000. Okay, here's why. And actually, that's a good point. when you enter the bandwidth on an interface, all right, make sure you know that the bandwidth is entered in kilobits per second. Bandwidth is entered in kilobits per second. It shows up in kilobits per second in the output. So if I go into an interface, let me go ahead and open up my file here. My packet tracer file. Let's see, study guides. Bear with me a second. I'm opening up the file. Now it opens twice. So here's my router. And if I do a show interface gig 00, show interface GI00, I can see that the bandwidth on this interface is 1 million kilobits per second. Okay? Now, if I come into my interface, config T, interface GI00, and I type in bandwidth 1000, do show interface GI00, it should change to 1000. And sure enough, it did. Simple. Right? Now, that doesn't mean I made my gig interface a meg. Again, it just changes how it's being evaluated. Aren't there serial links that reach gigabit speeds today? So does it mean that serial links always take longer to transmit? All right. Yes, it does take longer to transmit, and it's there are serial links that can be bonded together, or can use different types of encapsulation to make them operate faster. But like MLP, right? Bonding multiple PPP links together or whatever, but it doesn't get away from the limitations of the hardware, right? Serialization delay is still slower than gigabit Ethernet, fast Ethernet, and so on. Okay? Right, so I'm not sure why Arnold, yours didn't change to 1000. It should have changed to 1000. I'm going to change mine back. Okay. This is our topology that we're going to be working with. And in addition, you can change the delay value. Again, delay. Now, the thing about delay is, keep this in mind. Delay is written in tens of microseconds. So if I put in a delay of 1000, I have to multiply that times 10 to see the value in microseconds, right? So a delay of 1000 actually results in a delay of 10,000. Because in the output, it's in microseconds. In the configuration, it's in tens of microseconds. And then in the formula, it's in tens of microseconds. Right. So the smallest increment that you can adjust delay by is 10 microseconds. You can't set the delay by values of 1, in other words. Huh? Well, I know. Why not make them the same? Yeah. I agree. But remember, delay is not a function. The delay under show interface is not really a function of Eigrp. It's a function of the interface. What they should have done is just simply make the formula match the interface, right? And the command as well. So in order to manipulate paths, in order to manipulate metrics in paths, we can manipulate bandwidth, we can manipulate delay. All right? As I mentioned, all of this stuff, the metric, the calculation, successor, feasible successor, feasibility condition, everything else is a direct result of the diffusing update algorithm, which is the algorithm that we use for Eigrp. It provides loop-free paths and loop-free backup paths, meaning successors and feasible successors. It does bounded updates, incremental updates. It runs this thing called the dual finite state machine, which does all of these finite state machine calculations, right? All of these evaluations of paths, looking at different metrics, different values, and it tracks these different paths, and it uses metrics to determine the best path. The routes with the least cost path go into the routing table. Those are my successors. And then we maintain a list of backup paths, but we predetermine whether or not those backup paths are valid by going through the feasibility condition check. So if the primary path fails, we immediately start using the backup path instead of going through the query process and trying to identify whether or not that path is in fact valid or not. Okay, so here's our topology. We are going to be doing IPv4 and IPv6 in this lab. We're going to configure Eigrp for IPv4. We're going to configure Eigrp for IPv6. All right. The file that you have, which is the file that you downloaded, for those guys on YouTube, I'll post a link in the comment section so that you can download the file and do it as well. Let's take a look at this topology, all right? And it's very important because this is the topology that you will see, all right? So let's analyze this topology and see what it looks like. We've got 6 routers. So this is a pretty robust network. I mean, compared to what you guys started with on Monday, this is pretty intense, right? I mean, this is a lot of stuff. So we got 6 routers. We already talked about the neighbor relationships. Router 2, for example, should have 1, 2, 3, 4 neighbors. Router 6 should only have 1 neighbor. Router 1 should have 2 neighbors. By the way, I'm calling them router 1, router 6, router. If you look at the IP addresses, they all match the router number, right? So all of router 4's interfaces are 10.4.4. All of router 5's interfaces are 10.5.5, etc. Get the idea? And of course, we're going to do the same thing in IPv6. Now, if you look at IPv6, I kind of mirrored the IPv4 configuration for the IPv6 addresses, but 2001:10:4:4 is not the same as 10.4.4 because 10.4.4 is decimal. 2001:10:4:4 is hexadecimal. Even though it looks similar, it's hexadecimal. So what is the network, the IPv6 network for that LAN? Not the IP addresses, but the actual network ID. What is the network ID for that LAN? 2001, 192, 168, 123. Isn't that 64 bits? It looks like decimal. Don't let that confuse you. It's hexadecimal. All right? I didn't do the 2001 ACAD, whatever. I made it match the IPv4 counterpart, but they're completely unrelated to each other. So the IPv6 prefix for this LAN is 2001:192:168:123. This network is 12. This network is 13. This network is 10.1.1. This network is 192.168.16, and so on. Now here's a good question. On router 3, assuming that I've configured my entire topology, everything is done, I've set up Eigrp on every router, how many routes should show up on router 3? Oh, by the way, we're also going to have our loopbacks participating in routing as well. For all intents and purposes, just assume that those loopback interfaces are other networks. Right? Remember, a loopback interface is a virtual network on a router, a virtual interface. But we've created them in this topology to basically just add more networks to our domain without having to add more routers. So again, let me ask the question. Assuming that everything is running EIGRP, assuming the loopbacks are included, how many routes should show up on router 3 with a D next to them? D is EIGRP. Think about it before you answer. How many routes should show up in router 3's routing table with a D next to them? Giving you guys a little bit to talk about that and kind of calculate something. I said routing table. Okay. I said how many routes will show up in the routing table with a D next to them. And I got all kinds of different answers. I got 5, I got 9, I got 4, I got 7, I got 10, I got 1, I got 10. Okay. Well, let me put you guys out of your misery. Remember, the purpose of a dynamic routing protocol is to learn about everything that I'm not connected to. I am connected to this network, so that doesn't matter. I'm connected to this network, so that doesn't matter. And I'm connected to this network. Remember, that network is the whole LAN. So those would all show up in the routing table as a C. So some people may want to change their answer because anything that is not connected needs to be learned. Anything that is not connected needs to be learned. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Oh, so the local loops would be looking like external networks.
They're not external networks. They're not connected networks. Are those loopbacks connected to router 3? No.
No, they're connected.
They're connected to the routers that they're a member of. Right? Any network that is not connected has to be learned. All right? So congratulations to those that said 10. All right? Some of you were close. Some people said 1 or 5. Obviously not close, but all right? You guys understand, though, what I'm saying? Because right. Well, those are still remote networks. They're virtual networks, but they're still remote networks. The reason why I'm asking this is because I always get the question when we're doing, because we're about to start configuring this, I always get the question of, well, how do I know if I did it correctly? Right? Well, the quickest way to know if you did it correctly is to see if you have all your routes. But obviously, there's a progression to troubleshooting. We have to look at our neighbors, we have to look at our topology table, we have to look at our routing table, and so on. So we are getting close to lunchtime, so I want to get started on the configuration. And then after lunch, we'll do all the verification, and then we'll move on to OSPF. But so let's go ahead and get started. We have a question. So we see only remote networks, no directly connected networks. Directly connected networks show up in the routing table with a C because they're connected to the router. Anything that's not connected needs to be learned. So we still see the connected routes, we just don't see them as EIGRP routes. All right, here we go. How do we configure this? Just like in RIP, we need to go into router EIGRP. Now, before you guys actually start doing the configuration, which I'm going to request that you do before we break for lunch, just listen and watch what I'm doing up on the board before you actually start the configuration. Because I'm showing you both V4 and V6. Remember, we're configuring both protocols now. Configure terminal. Obviously, we know what that is. Router EIGRP, just like router RIP. When we wanted to configure RIP, we typed router RIP. But the difference here is we have to pick an autonomous system number. And that autonomous system number is, you pick it at your choosing, right? So you can pick any number from 1 to 65,535. We're going to use 1 in our topology, but there's no difference between one number or the other. They all mean the same thing. As long as they match on all the routers, that's all that matters. Okay? Now, before I look at IPv6, because this is v4, this is v6, I'm going to do all the v4 stuff, and then I'm going to go back and do all the v6 stuff. So the first thing is to go into router configuration mode. The next thing is to put in your network statements. Okay? In RIP, we did the same thing, didn't we? We put in network statements. But in EIGRP, you have a couple of options. So I'm going to describe what you can do with EIGRP in your network statements now. Let me open up Notepad, maybe, if it types. I don't know what's going on with my computer. It's running really slow right now. Oh, come on. Do I have Notepad open? I do not. All right. Why isn't it typing? All right. So in RIP, we did network, say, 10.0.0.0, right? And in RIP, what would that do? That would say any interface that starts with a 10 address would be running RIP. And I could say network 172.16.0.0, and it would mean the same thing. You don't need to be building this topology from scratch. This topology is already built. So hopefully you're not trying to build this topology from scratch. Please download the one that's, because it will take you forever to put in all the IP addresses and everything else. All right?
We're only building the router.
All we're doing in this is configuring EIGRP.
I didn't show like the protocols.
You don't have any protocols, right? Okay? So these are what we call classful network statements. And in EIGRP, you have the ability to enter classful network statements. It doesn't mean that the protocol is classful. It's just a way of entering the network statements so that all the routers or all the interfaces that are part of that are running EIGRP. But in EIGRP, we also have the ability to create network statements that are scoped. In other words, that include some interfaces but don't include other interfaces. And we do that by using something called an inverse mask. Some people call it a wildcard mask, but that's not completely correct, because unlike access lists where the bits can be anything, in network statements they have to be consecutive zeros followed by consecutive ones. So you can't just put ones and zeros indiscriminately across the mask. Okay? So if I said, for example, network 10.10.0.0, 0.0.255.255, right? What do you think would happen? What do you think, what interfaces would be running EIGRP? Anything that starts with 1010, that's right. You've had the benefit of going through the access list discussion. It essentially means the same thing. Zeros in the mask mean I care. Ones in the mask mean I don't care. So any network, any interface on any router that starts with 1010 is now going to be running EIGRP. You could do something like this. Network 10.10.10.5, 0.0.0.0. What does that mean? Any interface with that IP address is going to be running EIGRP. You can do something like this, 192.168.0.0. Now 192.168 is normally class C, but now I can use this mask to say any interface that starts with 192.168. So you can be really selective on what networks are running EIGRP, what networks are not running EIGRP.
So that's my internal corporate subnet class subnet. That's it. That's the only statement.
That's the only statement you need. Exactly. All right. That's the only statement you need. So it's very useful. You have a lot of flexibility. Now, a lot of people say, well, what should I do? What would be the best practice? And for me, honestly, I only want network statements to include interfaces that I want to run EIGRP. I don't want to put in some generic network statement because somebody might add a loopback or somebody might add another interface later, and it will automatically start running EIGRP, which I may not want to happen. So I like to be a little bit more specific with my network statements than some people. I mean, you could do this, network 0.0.0.0, 255.255.255.255, which gets converted to 0.0. That basically is like everything. Any interface that exists on this router runs EIGRP. Okay? So there's no golden rule on how you should enter your network statements. But you should think security and think about scoping. Honestly, if you use host-specific network statements, that's going to be your most secure option. I don't care how you guys decide to do it in your topology. For example, on, let's take a look, router 4 here. Actually, let me go back to the diagram. On router 4 here, at a minimum, how many network statements am I going to have, assuming I'm not using the quad 0? At a minimum, how many network statements would I have to have on router 4? The one that has all the 4s. How many network statements would I have to have at a minimum? 2. Right? Pat, it could be 1 if I'm using the quad 0, but it can't be 1 if I'm not. So network, I could do network 10.0.0.0, and I could do network 192.168.123.0. I used classful ones in this case. I didn't use wildcards. You don't have to use wildcards. If you're just using classful network statements, don't use a wildcard. To me, what would be the preferred? Network 10.4.4.4, 0.0.0.0, network 10.4.4.5, 0.0.0.0, network 10.4.4.6, 0.0.0.0, and network 192.168.123.0, I'm sorry, 123.4, 0.0.0.0. It's a lot more work. Well, not a lot, 2 extra statements. But at least I know for a fact that if somebody adds another loopback to this router, or if they add something else, it's not going to automatically start running EIGRP. See what I'm saying? Is there a reason to run EIGRP on the loopbacks? If I want them to show up in the routing table, yes. Otherwise, they won't. Do I need passive interface on router 4? I don't technically need it. I don't have any LANs. The loopbacks don't really count. There's no host there. But you're right. If normally, you wouldn't just have a router that's not connected to anything. So on the LAN side, you would have passive interface. Yes, it's not required for functionality, but it is best practice. Right. Do you guys understand the concept of these network statements and how you can manipulate a wildcard mask, inverse mask, to be able to manipulate what routes, what networks are part of EIGRP and what are not? If not, let me know and I'll explain it again. Because, by the way, this is exactly how it works in OSPF. OSPF uses inverse masks. And in OSPF, you have to use an inverse mask if you're using network statements. All right? What if I put in a network statement of network 192.168.0.0 and just hit return? I'm thinking, my thought process is, okay, I'm going to include any networks that start with 192.168. But without a wildcard, it assumes class C, which means I would actually have to have a network that has a 0 in it, in the third octet, which I don't, which means it doesn't do anything. Okay, so network 10.10.10.0, 0.0.0.3. Which interfaces are going to be running Eigrp? 1, 2, 3, and 4. It's just like wildcard masks and access lists. It's amazing how all this stuff ties together. Now, it's not very practical because if there were loopbacks, we could do that. 4, 5, and 6 I could do, but it would be 4, 5, 6, 7, and 8 because I'd have to do a block of 4. Yes, sir. Oh, because I could have done this. Network 10.4.4.4, 0.0.0.3. And that would include 4 through 7. Four would be included. That's what I'm beginning with. No, 0 through 3 would be included here. Yeah. I said 4 total.
Yeah.
0 through 3. What you cannot do is you cannot do this. Network 10.4.4.4, 1.0.0.3. These are not wildcard masks like access lists. So they have to be inverse masks, which means they have to be consecutive zeros followed by consecutive ones. Okay? So that's how you enable Eigrp in IPv4. All right? Now I'm going to show you how to do it in IPv6, and you're going to love me for it. In IPv6, it's much simpler. There are no network statements. First of all, you have to turn on IPv6 routing, which we had talked about before, IPv6 Unicast routing. Then you turn on you would configure Eigrp, IPv6 router Eigrp1. Same thing, we pick an autonomous system number. It doesn't have to match the v4 autonomous system number. But you have to specify, well, we don't have to in this case because we're dual stacked, but if you were just running IPv6, you'd have to put in a router ID. Now, I'm not going to talk about what a router ID is in this lesson because in Eigrp, quite frankly, the router ID doesn't play much of a role. But in OSPF, the router ID is very important. It plays a huge role. So we will talk about the router ID in OSPF in much more detail. You have to do a no shutdown. The Eigrp process is shut down by default in IPv6. And then if you want to enable Eigrp on the interfaces, instead of doing network statements, all you do is you go to the interface that you want to run Eigrp, and you type IPv6 Eigrp1. 1 is the autonomous system number. So you literally enable Eigrp directly on the interface. No network statements. That's kind of cool. And you can see from the output here, as soon as I do that, we already know what a link local address is. A link local address is the auto-generated address, the EUI64 generated address for all my link local communication. I've got a global unicast address on the interface, which I assign. Here's the network ID for the interface. And then all of a sudden you see that the router is participating in all these different multicast groups. FFO2:1 is all IPv6 hosts. FFO2:2 is all routers, which was initiated when we did the IPv6 Unicast routing command. And then it joined the Eigrp group, FFO2:A. All right? So that's how we're going to do our implementation. We are going to pause here for our lunch break. I was hoping that we would get into the actual configuration, but we'll do that right after lunch. We've got a little bit more, maybe another half an hour to talk about Eigrp, and then we're going to get into OSPF. So let's take our lunch break. So what we're going to do now is I'm going to go through, you guys have already done this during the break here. I'm going to go through and start configuring all of these routers. And I'll start with IPv4, and then I'll move on to IPv6. And I'm not going to use a uniform configuration approach here because I want to show you guys some of the different ways that you could potentially go through and configure these routers. And not one way or the other is necessarily better or worse. It just depends on what your overall objective is. So I'm going to go ahead and get into, I'm just going to start from the router on the left and move to the right. And what I'd like you guys to do is, as I go into a router, you guys go into your router as well, the same router. And when I run some verification commands, you guys, of course, will want to run the same verification commands. So I'm in router number 4. And the first thing I'm going to do, and this is typically what I would do in a real world as well, is I'm going to do a show IP protocols. And I want to do that because I want to make sure that I'm not already running any other routing protocol, because there might be a conflict potentially if I am running some other routing protocol at the time. Clearly I'm not, because show IP protocol shows me that I am not running any routing protocols. Now the other thing is, I already know that I want every interface on this router to participate in Eigrp. And I don't want to have to go back and forth between the diagram and the configuration to try and figure out what network statements I need to put as well. So what I'm going to do is I'm going to do a show IP route connected. And what that does is that very quickly gives me all of my connected interfaces, and I can build my Eigrp configuration right from that list right there. So I can come in here and say config T, router Eigrp1, network 10.444, 0.0.0.0, network 10.445, 0.0.0.0, network 10.446, 0.0.0.0, and network, if I can type, 192.168.123.0, 0.0.0.255. So what I've done, and Pat, you mentioned this earlier, is I've essentially taken what's configured on the interface, and I've created network statements that mirror that configuration. All right? So instead of doing the network statements based on host-specific addresses, I essentially just made my inverse masks the opposite of whatever the regular masks were on the actual interfaces. All right? So I've now configured Eigrp on router number 4. Should I see something other than the PowerPoint? Yes, you should see. Okay. All right. You should see me working on the screen here. Okay. All right. So that is router 4. Is it delayed? Are you on the WebEx? That's okay. Don't worry about it. You guys can see me doing the configuration on the WebEx, right? Yes? No? Yes. Okay. All right. Can I move it over to the left? All right. There you go. Yeah, Merrick, you guys, look, you guys should have already done the entire configuration. That's what we were waiting for. I was waiting for you guys to do the whole configuration. We weren't just sitting around doing nothing. That was your lab time. So hopefully you can keep up with me. All right, because now I'm moving on to router number 5. All right. No problem. So I am going to do a quick show IP protocols on router number 5. Of course, you guys won't get a blank here, hopefully. I'm going to do a show IP route connected real quick to see which interfaces are in this router. And I'm going to do a config T, router Eigrp1, and network 10. Now, in this case, I might decide, okay, I don't want to use specific wildcards. I just want to use classful network statements. So I could say 10.0.0.0 and network 192.168.123.0. All right, and of course, as soon as I do that, I get a neighbor adjacency with router number 4. All right. You do not need to disable auto summary because by default, it's already disabled in Eigrp. Remember, we're running 15 code on these routers. So Cisco no longer has auto summary enabled by default. I'm not suggesting that you guys should use different configuration methods every router that you go to. I'm doing that so that you can see different options for configuring these network statements. Okay? So I've got router number 5 done. Now I'm going to go into router number 2. Enable config T. Oops. Let me do the verifications first. Show IP protocols. Show IP route connected. So I'm going to do something a little bit different on this one. I'm going to do a mix of both classful and classless with wildcard. So config T router Eigrp1 network 10.0.0.0 network 192.168.0.0 0.0.255.255. So what I did in this case is I put in a network statement 192.168 with a wildcard of 0.0.255.255 so that I could run Eigrp on these two interfaces. All right, and any other interface that starts with 192.168. So that's router number 2. Router number 3. Show IP protocols. Show IP route connected. Config T router Eigrp. 1 network. And in this case, I'll just do a 0.0.0.0. Again, just another option. In this case, I said, let me just go ahead and run Eigrp on every single interface. Even interfaces that get added in the future. All right. Now we're going to do, excellent, Kalish. Now we're going to go ahead and do router number 1. Oops. That's what I was talking about on that test question. See, I typed ADN, and then it tried to do a DNS lookup. No IP domain dash lookup. Show IP protocols. Show IP route connected. Config T router Eigrp1 network 10.1.1.1 0.0.0.0 network 192.168 0.0 0.0.255.255. Okay. I'm doing it kind of quickly at this point, only because we're just doing the same thing over and over again. All right, I've got one more router to do here. Show IP protocols. Show IP route connected. Config T router Eigrp1 network 10.0.0.0 network 192.168.16.0. All right. So that is my entire configuration for EIGRP for IPv4. Now what I'm going to do is I'm going to go back across the whole topology, and I'm going to implement EIGRP for IPv6. These are completely separate protocol stacks, so you have to configure these protocols independently. All right? If I do a show IPv6 protocols, I can see that the only protocols I'm running are connected. Does anybody have any idea what ND is? ND. Neighbor Discovery Protocol. It's basically the IPv6 version of ARP, but neighbor discovery. All right? Yes, or the Fighting Irish, yes. So we are going to now configure IPv6. So config T, IPv6 unicast routing. This command enables the protocol stack on the router. It has nothing to do with EIGRP specifically. It is the entire v6 protocol stack for that router. All right? And then I'm going to do an IPv6 router, EIGRP1, no shutdown. I'm not going to set the router ID here. And let me just quickly explain. I don't need to technically set the router ID because I'm running IPv4. And the router ID is automatically selected by the router using one of those v4 addresses. Now in our OSPF lab and our OSPF discussion, we'll get into much more detail on the router ID when we go into that lesson. Then I'm going to do a quick show IP route connected because I want to see which interfaces now are in my router. Because remember, in IPv6, we don't use network statements. We go into the interfaces and we say IPv6, EIGRP, and the autonomous system number, and that enables the protocol on the interface. I'm going to go into Loopback 1, do the same thing, go into Loopback 2, do the same thing, and go into 00 and do the same thing. Kind of easier, isn't it? Simply just enable the protocol directly on the interface without having to figure out wildcards and whatnot. However, it's not as efficient because with wildcards, you can cover multiple interfaces at the same time. There isn't a way to do that in IPv6. You literally have to put that command on any interface that you want the protocol to run on. All right? So I'm done with router 4. I'm going to go ahead and go into router 5. All right. Config T, IPv6 router, EIGRP1. Oops, IPv6 unicast routing. Can't forget that. IPv6 router, EIGRP1. No shutdown. Do show IP route connected. Interface L0, IPv6 EIGRP1, L1, and interface GI00. And I should get an adjacency. Notice that the adjacency is formed using link local addresses, not global unicast addresses. Right? All of my routing updates, my links, my hello packets, they all are sent and received using these link local addresses and not global unicast addresses. So those link local addresses play a really, really important role in IPv6. All right, so I've done router 5. I'm going to go ahead and go into router number 2 now. Config T, IPv6 unicast routing, IPv6 router, EIGRP1, no shutdown, do show IP route connected, and interface loopback 0, IPv6 EIGRP1, interface GI00, and I got another adjacency, okay? I don't have any other interfaces on this router. Actually, I do. I have serial 021. So let's do interface serial 021 and IPv6 Eigrp1. All right, so I've now enabled Eigrp on router number 2. Let's go to router number 3. All right, config T, IPv6 Unicast routing, IPv6 router, Eigrp1, no shutdown. Do show IP route connected, interface L0, IPv6 Eigrp1, interface serial 021, IPv6 Eigrp1, interface GI00. There we go. Seems pretty simple after you go through it a few times, right? I did the no shutdown. If I hadn't done the no shutdown, I wouldn't have seen these adjacencies pop up. Sorry?
Oh, yeah, for the router. Yeah, I thought you were saying you didn't have to do much on the
No, they're already enabled. They've been enabled. Yeah.
I didn't do it. That's why I heard that.
Yeah. No problem. All right, router 1. Let's see. Show IP route connected. Config T, IPv6, Unicast IPv6, Unicast routing. IPv6 router Eigrp1, no shut. And interface LO0, IPv6 Eigrp1, interface serial 010, interface serial 011, and interface GI00. There we go. And lastly, router 6. Config T, IPv6 Unicast routing. Do show IP route connected. Interface LO0, IPv6 Eigrp1. Oops, I forgot to. IPv6 router. Eigrp1, no shutdown. Interface LO0, IPv6 Eigrp1. Interface GI00, and I should get a neighbor relationship. So there we go. I've completed the configuration for IPv4 and IPv6. Now I want everybody to go into router number 2, please. Everybody go into router number 2, and we are going to verify a couple of things. All right. Everybody go into router number 2, and we're going to verify a couple of things. All right, we're going to do a lot of things with this topology, but let's go ahead and verify our operation. Now, we already know that all the IP addresses were configured on these routers, all of the interfaces were turned on, so we didn't have to do any of that as part of the exercise. Okay, let's do a show IP Eigrp neighbors. Okay, now you should see 4 neighbors. If you don't see 4 neighbors, let me know or raise your hand or whatever, because you should definitely see 4 neighbors. Yes? Okay. Router 2 should have 4 neighbors, 3 on the Ethernet side and 1 on the serial side. All right. The first column that you see here, which has an H above it, that is called the host index column. Host index basically means from 0 to whatever, how many neighbors do I have? The lower the number, the older the neighbor. All right. Do you not have 4 neighbors? Oh, okay. All right. If you don't have 4 neighbors, fix it. All right. If you can't figure it out, let me know. So the first column represents the host index column. That means that this neighbor came up first, that neighbor came up second, this neighbor came up third, this neighbor came up fourth, and so on. The next thing you see is the address column. The address column obviously represents an IP address. It is the IP address of my neighbor. Okay. The interface column represents the interface that I go out of to reach that neighbor. So both of those columns actually are very useful because that represents essentially from a routing perspective what? It represents the next hop address and the exit interface. Doesn't it? The next hop would be the neighbor and the exit interface would be the interface column. The hold time is how long I'm going to keep this neighbor in the table if I don't get a hello. Now, if I keep revising my output here, you can see that those hold timers go from 14 to 13 to 12 to 11 to 10, back to 14 to 13 to 12 to 11 to 10. Well, guess what's happening? Remember, our update timer is 5 seconds. And our hold timer max is 15 seconds. All right? So we should never really see the timer go below 10 seconds because we're getting an update every 5 seconds. And that's what you're seeing as you refresh that screen. All right? Uptime is how long the neighbor's been active. And then smooth round trip time, retransmission timeout, queue count. Those are reliability mechanisms and retransmission mechanisms that are used in the Eigrp. We learn more about those variables in the CCNP routing and switching course. So I have 4 Eigrp for IPv4 neighbors, and the command that I used to verify that was show IP Eigrp neighbors. If I want to do the same thing in IPv6, show IPv6 Eigrp neighbors. Now, what's cool about this is that the table represents exactly the same information. It represents exactly the same information. Host index, neighbor's address, interface I go out of to get to that neighbor, the hold time, the uptime, etc. So the wonderful thing about learning about Eigrp is that you don't really need to learn all about the fundamental principles of Eigrp again for IPv6. All the stuff we talked about, successor, feasible successor, feasibility condition, all of the characteristics of Eigrp, it's all the same in IPv6. However, as you can see, the link local address is used instead of a global unicast address for the neighbor relationship. Now, for me, that's a little annoying because I can't tell from that list which router is which. I mean, it's really kind of impossible to say, oh, that's router 4, that's router 3, and that's router 2. Right? Here, it's pretty simple. Router 4, router 5, router 3, router 1. So a little trick of the trade that I will show you about IPv6 is that the link local addresses do not have to be EUI64 addresses. I don't expect you guys to make this change. I'm going to go ahead and make this change real quick just to demonstrate this concept. Config T. All right. interface GI00, IPv6 address. So what I'm going to do on this router is I'm going to change the link local address to something that I can recognize. Yes, what's up? Show IP EIGRP neighbors. All right. IPv6 address FE80:4 link local. There's nothing wrong with doing that. You can make your link local addresses anything you want. Of course, they have to start with FE80. But now, when I look at the neighbor relationship on router 2, I will see that that neighbor ID is going to be that FF02:4. So I could do the same thing here. I could go into interface GI00, IPv6 address FE80:5 link local, and I can change that link local address. And then I can even do the same thing on router 2. Well, let's do router 3 first. Interface GI00, IPv6 address FE80:3 link local. Now when I go into router 2 and I do a show IPv6 EIGRP neighbors, I can see router that this is router 4. I can see that this is router 5. I can see that this is router 3, and so on. All right? So it works pretty well. Works pretty well. Some of the old neighbor relationships had to clear out, or at least the stale ones. It took 15 seconds or so. But obviously I didn't do router number 1. But it's very cool. All right. What's even better is that in router 2, if I do a quick show IP route connected, config T, interface serial 021, I can say IPv6 address FE80:2, because this is router 2, link local. And then I can go into interface GI00, and I can say IPv6 address FE80:2 link local. In fact, I can make every link local address on this router the same address. Why? Why am I allowed to make every single interface the same link local address? Because they're link local addresses. They only matter on the wire. So you're not going to get a conflict because one link local address on one network has nothing to do with another link local address on a different network. Does that make sense? In other words, the link local address that router 2 uses on this LAN is completely independent from the link local address it uses on this serial link. It's called link local for a reason, because it's only used on the link. So you can make them all the same. Does that make sense? All right. The only thing you cannot do is have a link local address on router 2 on this serial link that's the same as a link local address on router 1 on the serial link, because then you'll get an IP address conflict between those link local addresses. How many of you guys caught all that I just did? Anybody? All right. All right. Let's go back to our lecture here. Can't open Packet Tracer. Well, that's fine. You can always go back to our YouTube channel and watch it again and work on it while you're watching the video. All right. What about automatic network summarization in EIGRP? We know what auto summary does. It forces the router to act like a classful router, even though it might be classless. EIGRP technically does the same thing. We didn't disable the auto summary feature, but if you do a show IP protocols, you will see that automatic network summarization is disabled by default, which is why we didn't have to concern ourselves with it. But look at what the effect of auto summary is, all right? I do not want you guys to make this configuration change, but I do want to show you what I'm talking about here. Let me go back to the topology diagram. We've got these loopbacks on, actually, let me go ahead and use router 5. We've got these loopbacks on router 5, correct? 10.5.5.5 and 10.5.5.55. Okay? Now, if I go over to router number 1, and I do a show IP route, EIGRP, let me make this a little bit bigger, I can see 10.5.5.55 and 10.5.5.5. I would expect to see those because they're part of EIGRP, they're being advertised, etc. Agreed? But if I come into router 5 and I go into the EIGRP routing process and I type auto summary and I come back to router 1, the 10.5.5.5 and the 10.5.5.55 networks disappeared because they are now included in this subnet. That router is no longer advertising the classless subnets. It's simply advertising the classful network of 10.0.0.0/8. Now imagine that the entire topology was doing that. Everybody would be advertising the 10.0.0.0/8 network. That would be really bad, wouldn't it? So make sure that you do not have, let me show you what it looks like under the router configuration. Make sure you do not have this auto summary command turned on because you're going to get routing issues. All right, so I'm going to turn that off, no auto summary. And it is off by default in EIGRP in the newer versions of iOS. Has nothing to do with the network statement. It wouldn't matter. Right, the network statement has nothing to do with how networks are advertised. It's just basically just turning on a light switch. Because I put in auto summary. That was the point, right? It is Friday the 13th, I can tell. Everybody's acting weird today. All right. All right. So obviously, in order to disable that automatic network summarization, we're going to use the no auto summary command. We don't really have to use that now because it's simply not, it's not on. Maybe on the test it might be on. That might be one of the problems you run into, but it's not on. Okay? Passive interface. Now, the way passive interface works in EIGRP is the exact same way it works in RIP. If you make an interface passive, it suppresses the protocol from running on the interface. It doesn't mean that that network still won't be advertised in the routing updates. It just makes the network passive. So if I, for example, come into router 6 and I go config T router EIGRP1 and I say passive interface GI00, what's going to end up happening is my neighbor relationship didn't fail because I'm in hold down state now. But after 15 seconds, my neighbor relationship expires. All right. Now, if I do a show run, I can see that the 192.168.16 network, which is gig 00, is still part of Eigrp. But because the interface is passive, it's no longer sending hello packets, which means that the router on the other side basically thinks that I don't exist anymore. Does that make sense? So, of course, you don't want to make interfaces passive that attach to other routers in the network. The only types of interfaces you would want to make passive are interfaces that go to LANs that don't have any routers. We don't happen to have any of those in our topology. All right? All right? You guys understand passive interface, yes? We talked about it a little bit with RIP. We talked about it with the Eigrp. We'll see it again with OSPF as well. Again, you can do passive interface default, or you can do passive interface on the gig interface. You know, make sure that you're careful, though, how you're running that passive interface command. So if you guys happen to be doing this lab a little bit later on, we've got some verifications that you can run. This is the first thing you should always do when you're troubleshooting the protocol. Make sure you have neighbors. Make sure you have neighbors. And you should literally have a neighbor for every physically attached router. Switches don't count, of course. All right. We've already done this verification. I don't need to talk about this table because we've already talked about the host index and so on. What is the next thing that I want to verify? Once I've verified all my neighbors, how about my topology database? How about verifying what I'm actually learning from the neighbors? Remember, these data structures are built in consecutive order, right? Neighbor table first, then topology table, then routing table. Here is the topology, the neighbor table, excuse me, for IPv6. Simply replace the IPv4, or excuse me, replace IP with IPv6. Make sense? The nice thing about this and the great thing about this is that the output is identical. It doesn't change. Host index, link local, gig interface, VLAN, uptime. It's great. We already know how to read all this information in IPv4. We simply read the same information in IPv6. All right? All right. Show IP protocols. If you guys want to run this command, you can, or you can just simply look at the screen. Show IP protocols we used in RIP. Show IP protocols allows us to verify our routing protocol state, right? What autonomous system number do we have? What are our K values? How many, what's the variance? We'll talk about variance a little bit later. That's the value that allows us to do unequal cost load balancing. We'll talk about that. Automatic network summarization is not in effect. Maximum paths 4. You guys remember what that was for? Maximum paths 4. That allowed us to identify how many paths we're going to load balance across if we have equal cost paths. The other interesting thing is when you look at routing for networks. Routing for networks is essentially a reflection of the network statements that you put in when you configured your protocol. So I can see in this case I used a couple of classful statements and I used a wildcard mask of 0.0.0.0 because those routing for network outputs there directly relate to the network statements that I put in the routing process. It's excellent. It's good stuff. All right. Show IPv6 protocols. Same kind of output. We already saw what connected and neighbor discovery was. We can also see now we're running Eigrp1. These are our K values, variants. These are the interfaces that are running Eigrp for IPv6. Because we don't use network statements, we see that we've implemented the protocol directly on the interfaces. Maximum paths of 16, same as maximum paths of 4, but in this case, just a lot more. And then the internal and external administrative distance values for Eigrp. It's good stuff. All right. Now you can jump right to the routing table, and you can take a look at the routing table. For example, if I asked you, based on this output, right? Based on this output, how does router 1 route to router 5? Look at the table. How does router 1 route to router 5 in this case? Let me give you some choices. Well, let me ask you this first. Is it doing a single path routing or is it doing multipath routing? Multipath routing. How can I tell that? Well, if you look at the routes, here's the 10555, here's the 10555, right? You'll notice that we have two different paths under the network. You see that? So 10555 is router 1 is reaching 10555 through router 3 and router 2. I know it's router 3 and router 2 in this case because of the 13.3 and the 12.2. Is it doing it with equal cost metrics or is it doing it with unequal cost metrics? You guys say equal, right? Why is that? Because that is the metric. If the answer was unequal cost load balancing, then those numbers would be different. And we're going to make them different. We're actually going to make them different. And then we're going to use variance. All right? All right? We're going to manipulate some values later on and kind of mess around with some of these metrics and do some calculations, and then we'll wrap up the chapter. All right? The next thing is the V6 routing table. It looks confusing, right? It looks confusing. And I imagine if you went to your routers and looked at your V6 routing table, it would look even more confusing because your link local addresses are EUI64. But in reality, it's the exact same thing, right? If I come into router 1 here, and I do a show IPv6 route, Eigrp, oops, show IPv6 route. You can use the Eigrp, packet tracer doesn't like it for some reason. So what about the equivalent of the 10555? I can see it right here, right? You guys agree? And I can see that it does equal cost load balancing across these two links. So the format of the table is slightly different, but the overall concept is exactly the same. Those link local addresses are simply next hop IP addresses. The serial 001 is my exit interface, and the destination prefix is, not Siri, the destination prefix is 2001:10:5:5:5. And in fact, if you take a look at this, for the 1055, 2298112 is the metric, and over here, 2298112 is the metric. So even the metric calculations are the same between both protocols, between both stacks. I guess my point is you don't have to relearn everything when you go to IPv6. All the theory, all the fundamentals, everything about the algorithms, everything about the metrics, it's all exactly the same between protocol stacks. The next thing we want to look at is our topology table. Our topology table. Remember, our topology table is a database that describes everything that I've learned from my neighbors. It describes everything I've learned from my neighbors. Now, if I come in here and I look at 10.5.5.5, right? Right here, here's 10.5.5 and 10.5.5.55. Sure enough, we see that the feasible distance is 2298112, which is the metric. That makes sense. We have two successors. What does that tell me? Equal cost load balancing. I've got two paths that are being used. All right. Now, and by the way, that's router 2 and router 3. Those are the neighbors. In the parentheses here, what you're looking at is the feasible distance, which is the first number, and the second number is reported distance from that neighbor. So for router 3, the feasible distance for that path is 2298112. The reported distance is 130816. For router 2, 2298112, 130816. So these paths look exactly the same. Now you'll see some codes up here at the top of the page. Those codes indicate the status of the data in the table. P, which is what we see here, lots of P. P means passive, which means that we're converged. We're not actively looking for a new route. We didn't lose a route, and now we're trying to figure out where the new route is. Okay? All right? Does it make sense? Awesome. Now, when you run this command, show IP Eigrp topology, when you run that command, all you're going to see in the output are successors and feasible successors. You will not see the other routes that don't qualify. They're still there. They're in the database, but you won't see them. In order to see every single route, you have to use the command show IP Eigrp topology all dash links. All dash links will allow you to see all of the networks. Does that make sense? I mean, check it out. 192.168.1.0, one successor, all right, with a feasible distance of 217.2416. So that's clearly this path is my successor path. Does the secondary path here, which is not a successor, does it meet the feasibility condition? Yes or no? Does anybody say yes or no? Does that secondary path, the one that goes through 172.16.3.2, does that meet the feasibility condition? Okay, so I have a couple of yeses. I have some people kind of between yes and no. And I have some people that could care less. All right. Does it meet the feasibility condition? And Merrick says he doesn't know. That's good. That's why you're taking the class. All right? And the answer is no, it does not. Yes, the second number in the parentheses is the reported distance for that path. And if that number is greater than the feasible distance of my primary path, then the answer is no. That's how you can evaluate, sorry? No. Has to be less. So this is an example where I'm seeing a successor route, but I'm not, and I'm seeing a non-feasible successor route. Because the reported distance of that route, right here, is less than the feasible distance of the primary route. That's the feasible distance of that path. That's right. The 41026560 is the feasible distance of the 3.2 path. So obviously it has a much worse metric. And by the way, right? The feasible distance is the metric. 28160 is the reported distance for that path. It's always FD/RD. FD/RD. That's what you're seeing in the parentheses. That is right, Maynard. The reported distance, sorry? Advertised distance and feasible distance. So, let me rephrase. When it gets put in the routing table, you have administrative distance, which has nothing to do with the Eigrp metrics, and the metric itself, which is feasible distance. That's why I don't like to use the term advertised distance, because it gets confused with administrative distance. They're completely separate things. So we call it reported distance, which is the same thing as advertised distance, but it makes it a little less confusing. All right. All righty. I mean, think about what you guys knew about Eigrp before we started this lesson. Think about what you know about it now. Quite a bit. Yeah. Okay. We're not quite done yet, though. We've got a little bit left. All right. Summarization. Summarization. You know what summarization is? We had a lesson about summarization back in ICND 1. We know what auto summary is as well, which is a bad thing. But Eigrp is a classless routing protocol. So it includes the subnet mask information along with the routing updates, which means that we can essentially create these summarization boundaries that permit us the ability to reduce the size of routing tables. Okay? These are called supernets. They're aggregate routes that represent subordinate routes that are part of the aggregate. Okay? So let's take an example. You guys can configure this if you so choose. You don't have to necessarily. But let's say router 4 here. I want to summarize those 3 loopbacks, and instead of sending or advertising in the 3 loopbacks, I want to go ahead and just advertise in a summary. Now, if I go to router 1 real quick, and I do a show IP route Eigrp, I can see 10445, 10446, 10444, 5, and 6 there. So I'm seeing the individual loopbacks there. So what I'm going to do is I'm going to go into router 4. All right. Config T, interface, GI00. You always go into the interface that you want the summary to be sent out of. All right, and that's what we see on the diagram here. I want these loopbacks to be advertised as a summary out of that interface. Does that make sense? Because now I don't want to advertise the 3 individual routes. I want to send in one route that represents all 3 routes. All right, so I'm going to come back in router 4. I'm going to say IP summary address, Eigrp1. So I'm creating a summary route for Eigrp1, 10.4.4.4, 255, 255, 255, 252. We don't use wildcard masks for summaries. Okay. Now, why did I choose that particular mask? Because it runs 4 through 7, right. I'm trying to create a summary that includes network 4, network 5, network 6. Now it's a block of 4. I can't create a block of 3. So I've created this block of 4 addresses starting at 10.444 going up to 10.447. Enter. Refresh my neighbor adjacencies. Now if I go to router 1, I no longer see the individual 10.444 routes. I see the summary route. So I've essentially reduced the size of my entire enterprise's routing tables by putting in that summary. I could do the same thing for 10.5.5 and any other networks that I can summarize. I can still ping 10.444. I can still ping 10.445, and I can still ping 10.446 because it's using that summary route to get to those destinations. In fact, I don't know if this will work. We'll give it a shot. Debug, do debug IP ICMP. Ping 10.447, unreachable. And in fact, I saw those routes hit the router, or those pings hit the router. Because the 7 subnet is included in that summary, right? So even though 10.447 didn't exist anywhere in my enterprise, no 10.447 anywhere, the summary included 10.447. That's the only downside to summarization. There's the potential that you're going to start advertising networks that you don't own. Receive traffic you're going to throw away. And by the way, how is that traffic thrown away? We talked about this as well. The null 0 route, right? So I've created a summary on router 4, which means I should see a null 0 route in the routing table. Let's do undebug all and do show IP route. And sure enough, there is my null 0 route. So that 10.447 traffic is hitting this router, and then it's getting matched to that null 0 route and getting dropped. Yes. Remember, we match routes based on longest prefix. So that they don't. Right. It's not a list, it's a table. Because otherwise the 10.4.4 packets would be, or the 10.4.4.4 packets would be dropped. But instead, we're matching 10.4.4.4 to the /32 because it has a longer prefix. No, because that's just a network statement. It has nothing to do with summarization. You were just using that to include multiple interfaces in the Eigrp routing process. This is cool stuff. I mean, I love doing this stuff, and you know, the more you learn, and the more you can see how you can make this efficient and work, and it just does what it's supposed to do. It's pretty cool, right? It's pretty cool stuff. Obviously, in this lesson, we're not talking about summarization. We did that in a previous lesson in the IP addressing and the introduction to routing section. But you guys know why we have this down here, because we're looking for our common bit patterns, and that's how we create our summary address. All right. And like I said, I showed you guys this. You see the 10444/30. That's what's now being advertised, and we have the null zero route that was created as well in the router that's originating the summary. All right. What about IPv6? Well, it's exactly the same thing. We've been kind of repeating ourselves on that, right? If I want to summarize those IPv6 routes, I simply go into router 4, go into interface GI00, IPv6 summary address, Eigrp1. And in this case, I'm summarizing 2001, 1044, :4, :5, :6. So if you convert that to binary, our summary boundary is there. This is 16 bits, 32 bits, 48 bits, 64 bits, 68 bits, 72 bits, right? Well, there's a whole bunch in between, too. Remember, the :: represents a whole bunch of zeros. This is the host portion. This is the network portion. In the end, it ends up being 126 bits that are the same. Mathematically, summaries in Eigrp are calculated exactly the same way that they're calculated in IPv4, because we're dealing with binary. Even though the address is written in hexadecimal versus decimal, ultimately we're dealing with binary addressing. That is ultimately what we're dealing with. You guys should feel pretty comfortable with figuring out summary calculations. You guys should feel pretty comfortable with that. Okay? All right. And then we verify it the same way. Instead of receiving the individual routes, we receive the summary route. All right? Although I don't know why it's a /125 there. It should be a /126, because the only bits that don't match are the ones on the end, which are the last 2 bits of the address. Right? I mean, think about it. This is 4, this is 5, this is 6. Only the last 2 bits didn't. So I probably entered the summary address wrong in this case when I was verifying that output. Incidentally, you still get a null zero route. You still get a null zero route. It's cool. All right, just a couple more slides, gentlemen, then we are done with Eigrp. We'll take a break, and then we'll get into some OSPF. Load balancing in IPv6 and IPv4 for Eigrp. We use the maximum paths command. Now, equal cost load balancing is when the router identifies multiple paths that have the exact same metric, and then I distribute packets across those links whenever I'm sending traffic to that destination. In Cisco iOS, up to 4 equal cost paths in IPv4 or 16 in IPv6 will be load balanced, but we can use the maximum paths command to change that behavior. So for example, if I go under Eigrp and I change the maximum paths to 10, then that means I'm going to load balance across 10 paths potentially. If my goal is to disable load balancing altogether, I'll set the maximum paths to 1. We don't typically modify this value. We generally just leave it at its default. All right. How do you know if you're load balancing a path? Look at the routing table. If you see multiple entries for the same route, you're doing load balancing. You are doing load balancing. Now let's take a look at our topology here real quick. And this part I want you guys to participate in, not just follow along. So if I look at my routing table on router 1, show IP route, specifically, I'm load balancing 10.5.5.5 and 10.5.5.55. Does everybody agree with that? If I'm looking at that table, I'm doing equal cost load balancing for those two paths. You guys agree? Okay. Well, let's go through an exercise where we actually calculate how that is occurring. So I'm going to take a screenshot of this, and I am going to go into Paint. Let's see. What the heck is it? My search window's not working for some reason. I don't know. Yeah, I don't know why. Come on. Oh, it is it. Yeah. It would be nice.
Windows accessories, sorry, not Microsoft.
Windows accessories, okay. Where do you see it? Do you see it?
Windows accessories.
Oh, yeah. There we go. Okay. Wow, challenging. Okay. All right. So let me go ahead and clear up some of this stuff here because we need to put some stuff on this diagram. All right. And we don't need all this stuff on here to do that. So I am looking at the routes on router 1. All right. And the routes on router 1, of course, is this router right here. And the routes that I see are right here. So let me put that in the diagram. All right. So I've got these two routes, and we can see that for these two routes, there should be a D in front of this one. There we go. For these two routes, so I'll even make it line up for you guys, we have the exact same metric. 2300416 here, 2300416, 2300416, and so on. Everybody agree? So we are doing equal cost load balancing for those networks. Now, if you look at the path that we have here, that means that it's going through router 3 and router 2. And if you take a look at the path, that means it must be going this way, and it must be going this way. There's a line between here. I accidentally deleted it, but if you look at those paths, and you might say, well, wait a minute, those paths aren't equal. It seems like the bottom path should be better. Well, let's take a look at the math, and let's take a look at how we can manipulate this value. So if I take a look at the top path, if you remember, the metric is bandwidth times, or bandwidth plus delay, right? That's what the metric ends up being. And bandwidth is 10 to the power of 7 divided by the worst bandwidth along the path. All right, if I go into router 1, I do a show interface serial 010. I can see that the bandwidth is 1544 and the delay is 20,000. So that is the value at this point. You guys follow what I'm saying, right? I'm looking at the egress interfaces towards the destination. And specifically in this case, that is the value on this interface. Would you guys agree that it would be the same on that interface? Should be. It's a serial interface, right? And remember, when we're calculating metrics, it's only the egress interfaces that matter. This interface, this interface, this interface, and ultimately these interfaces. All right, move that over. That's all that should matter. So let me go into router 2 and do a quick show IP interface, show interface GI00, and let me grab the bandwidth and the delay for that interface. Oops, go Control C in this application. Another pet peeve.
Yeah.
So we've got the bandwidth and delay for this interface now. And would you guys agree that that's probably the same for the other gig interface? Right? So that guy's going to have the same bandwidth and delay. This guy's going to have the same bandwidth and delay on this side. So the only thing left is to check the loopback interface on router 5. So I'll go into router 5, show interface LO0. And the bandwidth and delay on this interface is this value. And we do count those interfaces. Those interfaces are our destination. All right, let's do some wonderful math. The formula for bandwidth in Eigrp is 10 to the power of 7 divided by the worst bandwidth along the path in kilobits per second. So it's 10 to the power of 7 divided by what? What is the worst bandwidth along the path in either path? 1544, which is going to equal 6536, but let's go ahead and do the math. 10 to the power of 7 divided by 1544, 6476. Remember, we dropped the remainder. So that's going to equal 6476. That's the bandwidth part of my metric. You guys agree with that? Now the delay formula is the sum of all the delays along the path in microseconds divided by 10. So I've got 20,000 plus 100 plus 5,000 is 25,100. You guys agree? Yes, Kailash, we'll get there. Or Kailash, sorry. 2510, 20,000 plus 100 plus 5,000 equals 25,100, and we divide that by 10, which equals 2510. So the metric equals bandwidth plus delay, and in this case, we multiply that value by 256. You always multiply by 256. Whether you do it to each individual value or you do it to the combination of values, it's up to you. So I'm going to take 6476, right, which is my bandwidth calculation, and I'm going to add that to 2510, and I'm going to multiply that times 256, 649036. Something I didn't do right. That's not correct. What did I do wrong? No, I didn't do something. Sorry? Oh, yeah. I didn't do the... So I'm going to have to do 6476 times 256. So I'll copy that. All right. And then I'm going to take 2510 times 256. And then I'm going to add this value, 2300416. $2300416. Hey, how about that? We calculated the metric. Huh? Yes. And by the way, the switches are transparent, which is why they don't come into play on the path selection. Now, let me ask you guys something. If I want to force the traffic to take the top path instead of the bottom path, at which point in the network can I change a value to do that? And what value should I change? I want the top path to be preferred over the bottom path. You guys agree that I cannot change these interfaces here, right? I can't change, I can't change those interfaces there because, well, those interfaces apply to both metrics. I can change the bandwidth. If I change the bandwidth of R2 or R3, that's going to be a pretty significant change because it has to be the worst bandwidth along the path. Right? If I change the bandwidth on R2 or R3, I would have to manipulate the bandwidth so much. And you can do that. I would have to manipulate the bandwidth to the point where it's worse than 1544. So that's kind of like working with a sledgehammer. From router 1, yes. I didn't say that. I didn't say that. This is the challenge. You know, when you're making changes like this, it very rarely will only affect one thing. So Pat's correct. I could change the bandwidth on the serial interfaces. I can make one a little bit better or make one a little bit worse. Right? There's lots of ways to do it. I could change delay values. I can increase or decrease delay values. Here's what I'm going to do though, because I want to accomplish two things. I'm going to manipulate the values on the gig interfaces. And the reason why I'm going to manipulate the values on the gig as opposed to the serial is because if I modify the serial values, I'm only affecting the feasible distance. I'm not modifying the reported distance. So I'm going to change the values here because I want to modify the reported distance because I want to show you guys something about reported distance. But you could do it anywhere. You just have to plan appropriately. You have to say, okay, if I change it here, what's the effect going to be? All right? Now, all that being said, if my goal was to get asymmetric routing, quite frankly, the link that I would modify is one of the serial links. Because remember, if you make a modification in one direction, it has no effect on the traffic flow in the other direction. Let's say I make this link better by changing the bandwidth on this interface to 2000. Then this path is preferred to get to the loopbacks. But this router will load balance to get back because the metric returning is not symmetric with the metric going out. Does that make sense? All things to consider when you're doing this type of route manipulation. All right, so let's go ahead, and I want to make the top path preferred. So what I'm going to do is I'm going to go into router 2, config T, interface GI00, and I'm going to say delay, right? Well, let me do this first. Do show interface GI00. The delay of this interface is already 100. Okay. So I'm going to put in a delay value of 9. Okay. I only delay by a slight margin, not by a lot, not by 91. I didn't decrease it by 91. I decreased it by 10 because it's in tens of microseconds. So if I do show interface GI00, my delay should now be 90. Because when you enter it in the command, it's in tens of microseconds. But I did make that path more preferred. The smaller the delay, the more preferred the path. If I come back to router 1 and I do a show IP route, you will now see that I am no longer load balancing to the 10555 network. I am now preferring the path through router 2. And if I do a show IP Eigrp topology, you will see that I only have one successor, but I have 2 paths. See how that works? And by the way, the reported distance is now different. This is my preferred path. This is my backup path. Does the backup path meet the feasibility condition? Yes. The backup path meets the feasibility condition 133120 is less than 2300160. So not only do I have a successor, I have a feasible successor. That make sense? Now I want to make it so that it's not a feasible successor. Actually, before I do that, I wanted to wrap up the discussion about this variance. Okay? Because now we're not load balancing. But if I add the variance, I will be load balancing again. So I'm going to go into router number 1, config T, router Eigrp1, and I'm going to say variance of 2. And now if I do a show IP route, Eigrp, I am now load balancing again. And I'm doing unequal cost load balancing. You can see it's unequal cost because the metrics are different. So what the heck is variance? It's very, very simple. It is a multiplier against the feasible distance. So if my feasible distance is 10, and I put in a variance of 2, then anything from 10 to 20 is considered equal. Does that make sense? Or the topology table. Of course, yeah. So you'll see two successors. It is post-algorithm. I've gone all through my calculations. See, I've got two successors. So in reality, anything, because I put in a variance of 2, and my best metric is 2300160, multiply that times 2, any number from 2300160 to 4.6 million is considered equal. So variance is not very granular. You know, variance is, well, it works on very large numbers. So now I'm going to make something break. They do not go 50-50. They, the algorithm, let me see if I can make this happen. I want to make the backup path even worse. So I'm going to make the backup path worse. And by putting in a delay of 10,000, which is 100,000 on this interface. So I've now made the bottom path worse, much worse. You cannot use non-integer values. They have to be whole numbers. So, oh, well, something happened. What the heck happened? I only have one successor now. Is it outside the variance? Yeah, the all-links command doesn't work on this. Is it outside the variance? Let me go see. Do show IP route. I can see if it's outside the variance. If I look at the routing table on, so 269.0560, it's not outside the variance. It's not more than 4 point. Remember, it's reported distance, right? There's another way to check this, by the way. If I come into router 1, serial 010, shut that down, do show IP route. All right, it is outside the variance, actually. Is it? No, it's not. Oh, yeah, it is. 4.8 million. It's outside the variance. So what can I do to fix that? Let me turn that interface back on. Notice how I checked that, right? I just turned off the other path to see what the metric was. What if I went into router Eigrp 1 and I did a variance of 10? Well, okay, that should definitely fall within the spectrum, right? Do show IP route. Still doesn't show up. Does anybody have any idea why? I know you guys can get there. Well, now the upper boundary is like 20 trillion because it's 2300160 times 10. 23 million. We were only at 4.8 million. No, there's no limit. Come on, guys. I know you know this. Let me go back to router 3. Do show IP route Eigrp 269.0560. That's the metric from router 3 to get to the 10.55 subnet. which, by the way, would be the reported distance to router 1, and the metric here is 2300160. It doesn't meet the feasibility condition. The reported distance has to be less than the feasible distance of the primary path. 2690560 is higher than 2300160. Now, I should be able to see that in my topology table, but unfortunately, Packet Tracer, well, it doesn't do the all-dash links. Show IP Eigrp topology. It does it. It accepts the command, topology all-dash links, but it doesn't report the output correctly. I should see two routes here. I should see the one that doesn't meet the condition. So unfortunately, Packet Tracer doesn't show us that correctly. But the reason why is not because of variance. The reason why we're not seeing the second route is not because of variance. It's because the route doesn't meet the feasibility condition check based on the reported distance. 2690560 is higher than 2300160. All right. So for troubleshooting Eigrp, of course, you want to look at your neighbors first. Show IP interface brief. We know what that command does. It allows us to verify the operational state of our interfaces. Show IP protocols, of course, and so on. And in IPv6, we do the same thing. The only difference is we're looking at IPv6 outputs instead of IPv4 outputs. All right. That concludes Eigrp.